What sparked the very first light in the cosmos? What mysteries lie hidden in the universe's long, dark age? How did the first stars shape everything that followed? In the hush of a clear night, the sky above stretches into infinity. Countless stars shimmer against a backdrop of darkness, each one a distant sun glowing softly. We stand under this silent dome of night, aware of how small we are in the face of that vastness. The Milky Way arches overhead, a pale river of starlight, hinting at the countless worlds hidden in its glow. In this moment, all of Earth's noise falls away, leaving only the quiet awe of the cosmos. It is almost impossible to truly grasp how enormous the universe is. Our minds reach for comparisons. The distance to our moon, our sun, the edge of our solar system. Yet these familiar milestones barely leave the neighborhood of our galaxy. Beyond the Milky Way lie billions of other galaxies, each filled with billions of stars. We imagine traveling outward, past swirling galaxies that look like tiny whirlpools of light, farther and farther, trying to comprehend distances so great that even light, moving at the fastest speed there is, takes millions of years to cross them. As we drift in this thought, the scale becomes overwhelming. Numbers grow absurdly large. 100 billion galaxies, 100 billion stars in each. Figures so vast they lose meaning. If each star were a grain of sand, how large would the desert be? If each galaxy were a single light in the dark, how many nights would we need to count them all? Our minds can only wander, sensing the immensity without fully understanding it. And within this endless expanse, we cannot help but wonder about what lies hidden in the far reaches, beyond what our eyes and telescopes have yet seen. High above, a shooting star silently traces a path, a tiny messenger from the depths of space. It reminds us that even in the stillness, the cosmos is not empty. There is movement and mystery everywhere. When we gaze into the sky, we are looking across both space and time. The faintest starlight we catch may have begun its journey millions of years ago, long before humans walked the earth. We are seeing the past shining down on us. The universe is so vast that its distances blur the line between then and now, between here and an unreachable there. Floating in these reflections, we feel a mix of humility and wonder. The vastness above can make our everyday worries feel small, dissolving in the face of something so much greater and older than we are. There is comfort in that realization, knowing we are part of a grand, mysterious cosmos, woven into its story by the simple act of observation and curiosity. Yet there is also a gentle mystery that tugs at our thoughts. We sense how much is unknown. We grasp only a tiny piece of a much larger picture. In the quiet night, under ancient starlight, we allow ourselves to accept that some things might always be beyond our grasp. And still, we yearn to know more. It is the vastness that humbles us, but also invites us. It whispers an unending invitation to explore and to understand. We can close our eyes and feel the depth of space stretching outwards, an ocean of stars and galaxies without shore. In that darkness, the unknown beckons softly, promising discoveries that lie just out of reach. Our journey into the cosmic enigma begins here, with this simple act of gazing upward and feeling the immensity press gently on our hearts. We will venture from the present into the distant past, seeking answers among the stars. For if we are so small in this great expanse? How remarkable is it that we can ask the questions at all? And as we take our first steps on this journey, the first question naturally arises from the darkness. How did all of this begin? Let us journey back in time, far beyond memory or recorded history, to the moment when everything began. In our minds, we peel away the layers of time, moving backwards through eons. Galaxies condense into a single brilliant point. Stars, planets, and dust, all drawn closer together as we rewind the cosmic clock. We go further still, past the formation of the first galaxies, past the birth of the earliest stars, past even the light itself, until all that exists is gathered into a space smaller than a single grain of sand. In that unimaginable beginning, the universe was concentrated into something so incredibly dense and hot that the laws of physics as we know them could not yet take shape. It is a moment hidden behind a veil our science cannot yet lift, often simply called the Big Bang. But the term bang is misleading. There was no sound in the emptiness, no air to carry a noise. Instead, there was a sudden expansion, an almost instantaneous unfurling of space and time themselves. One heartbeat there was nothing we can understand, and the next, everything burst forth in a searing light. We can try to picture it. A newborn universe, flooded with energy, so hot that atoms could not exist. Just a plasma of the most fundamental pieces of matter and light mixed together. In those first moments, space itself stretched and ballooned outward at a pace beyond anything we can truly imagine. What began as smaller than a mote of dust swiftly became as large as the cosmos we know now, all in a fraction of a second. It's as though the universe took a deep breath and expanded in one great sigh of creation. As the expansion continued, the brilliant glow began to cool. In time, minutes, hours, years, the searing brightness softened. Particles that had been racing chaotically began to slow enough to combine. The first simple atoms formed, tiny hydrogen and helium atoms that would one day coalesce into stars. With atoms came a remarkable change. The opaque glow of the young universe turned transparent. The blinding light that filled everything was now free to travel. This was the first light we can still detect even today, stretched into a faint microwave whisper that echoes all around us. For a brief time, the entire cosmos was aglow, filled with a warm light as the afterglow of creation spread outwards. But as the universe expanded and cooled further, that light faded. What remained was darkness and silence. There were no stars shining yet, only vast clouds of gas drifting through a black cosmos. The temperature had fallen so low that the brilliant radiance of the beginning dimmed below the threshold of our vision. The stage was set, and everything was in place for the next act. But the cosmic theatre was dark. In that darkness lived a profound mystery. We can describe how the universe expanded from an extremely hot, dense state. Our mathematics and physics take us back to a split second after the beginning. But the exact moment of birth, what sparked existence itself, remains beyond our reach. Did time even exist before this expansion? What lit the spark that ignited reality? We do not know. It is as if a curtain hangs over the first instance of time, leaving us with tantalizing questions. We stand at the threshold of the ultimate mystery, how something arose from what seems like nothing. Yet from that mystery came everything we are and see. All the galaxies, stars, and planets were seeded in that first moment. And now, as we envision the darkness that followed the initial light, we prepare to step into a time before any star had ever shone. The universe, newborn and expanding, drifted in silence, waiting for the lights to come on. Before any stars first sparkle, there was a deep night that lasted for ages. It is to this cosmic night, this chapter before the dawn of starlight, that we now gently venture. We find ourselves in a universe without light. After the initial glow of creation faded, an immense darkness prevailed. Imagine drifting through that young cosmos, some hundreds of millions of years after the beginning. There are no stars to guide your way, no galaxies yet shining in the void. Everything is quiet and cold. The only faint glow is the leftover whisper of the Big Bang's light, now stretched to invisibly long wavelengths. To human eyes, it would be perfect darkness, an endless midnight across the newborn universe. In this darkness, the universe was not empty, but filled with vast clouds of hydrogen and helium gas. They were the ashes of the Big Bang, spread out thinly across expanding space. Though it was dark, gentle forces were at work. Tiny irregularities in the otherwise uniform gas, just slightly denser spots, began to draw in more matter through the pull of gravity. Over countless years, those clouds grew denser and tighter, assembling the seeds of what would one day become stars and galaxies. It all happened in silence, slowly, like a whisper building into a quiet breath. No human eyes would ever witness this era, and no telescope can directly see it now. The darkness hides its secrets well. We can only reconstruct it in our imagination and with computer models, tracing how the first sparks must have formed. In the cold void, pockets of gas continued to collapse inward. As they did, they heated up invisibly at their cores. The pressure built quietly. The universe during this time was like a hushed theatre, the stage set and waiting for the lights to come on. Nothing yet stirred to break the black stillness. Yet, even without visible light, changes were unfolding that would transform the cosmos. Deep in the densest cores of these gathering clouds, the first star was preparing to ignite. We think these first stars, born from pure hydrogen and helium, were giants, much larger than our sun. They formed in a cosmos that had never seen starlight, so when they finally ignited, it was truly the first dawn. But until that moment, the darkness was profound. The temperature of space had dropped to a chilly glow, only a few degrees above absolute zero. Millions upon millions of years passed in this dark age, with the universe expanding and the silent work of gravity continuing. This era carries a deep mystery. We know it must have happened, yet we have never observed it directly. What did those first stars look like when they finally turned on their lights? How massive were they? And how long did they live? Did they form alone, or in clusters that would become the first small galaxies? We have hints and theories. We suspect the first stars lived short, brilliant lives and died in powerful explosions, seeding the cosmos with new elements. But no one yet has seen the glow of those earliest stars. Their light would have travelled for billions of years, only to fade by the time it reaches us now. As we drift in this imagined darkness, there is a feeling of anticipation. The universe, in its youth, waits quietly for its first sunrise. We hold our breath with it, sensing the moment approaching when the void will no longer be dark. It's a solemn and still place, but not a permanent night. The ingredients for illumination are there, hidden in the black. Eventually, inevitably, the first star will burst into light, and the long darkness will give way to a new cosmic dawn. That moment, the end of the Dark Ages, arrives with a brilliant unveiling, and with it, the universe's next great mystery begins to unfold. Before we continue further into the cosmic story, we must pause and look back to the very beginning for a moment. There is a perplexing chapter in the universe's first heartbeat that we only briefly touched upon. It's a mystery scientists are still trying to unravel, the strange episode of cosmic inflation. In that fraction of a second, just after the universe was born, something extraordinary is believed to have happened. The infant universe didn't just expand, it swelled at an almost inconceivable rate, far faster than anything we observe in later eras. Imagine the universe as an unimaginably tiny bubble at the moment of its birth. Now imagine that bubble blowing up to the size of a galaxy in the tiniest sliver of time. Far less than a blink of an eye. During this brief flash, space itself expanded faster than the speed of light could travel through it. There was no explosion outward in the usual sense. Rather, space was stretching, carrying everything with it. Distances between points ballooned so dramatically that something the size of an atom could have stretched to the size of a solar system almost instantly. This is the essence of cosmic inflation, a sudden, massive growth spurt of the universe. Why do scientists think this wild idea of inflation is true? It helps answer some deep riddles. When we look at the universe today, no matter which direction we gaze, space looks surprisingly uniform. The temperature of the faint afterglow of the Big Bang, the cosmic microwave background, is nearly the same everywhere. Without inflation, it's hard to explain how different far-apart regions that could never have exchanged light or information ended up so alike. Inflation offers a possible answer. Those regions were once so incredibly close together in the tiny early universe that they could influence each other before being whisked far apart during the sudden expansion. Inflation also neatly explains why space appears to be geometrically flat, and why we don't see a lot of the strange relics some earlier theories predicted. It ties up several mysteries in one bold theory. Yet, inflation itself remains mysterious. We have strong hints that something like it happened, but we don't know exactly how or why. What force or field caused space to inflate in that way? Physicists give the placeholder name inflaton to whatever might have driven inflation, but it remains a hypothetical concept. We don't know what this inflating substance or energy was, only that it must have behaved unlike anything we see today. Equally enigmatic is why inflation stopped. It had to slow down dramatically, transitioning into the more gently expanding universe we know, where stars and galaxies could form. What caused the universe to slam on the brakes after that initial surge? That is still unknown. Think of cosmic inflation as a dreamlike flash at the very start of time, a moment when the normal rules took a back seat and the universe raced ahead of itself. In that silent instant, tiny random fluctuations, perhaps from quantum processes bubbling in that small space, were blown up to enormous scales. Those subtle, uneven spots became the seeds for galaxies and clusters we see billions of years later. In a way, every galaxy in the sky today might trace its roots to the microscopic flickers of randomness amplified by inflation's giant breath. Contemplating inflation fills one with awe at how different the early universe might have been from our everyday experience. It reminds us that the cosmos keeps its oldest secrets well. We stand here now, billions of years later, with a vast universe stretched out around us, trying to piece together that fleeting moment when everything changed in an instant. The answers hide in the very limits of what we can test and observe. And as we ponder this rapid cosmic heartbeat, we also recognize that there are other invisible mysteries threading through the universe. Even in the calm, ancient space we drift through today, one of those unseen enigmas has been with us from the beginning and still surrounds us. The quiet, unseen presence of dark matter. All around us in the universe, there is something we cannot see, yet it holds the cosmos together in its silent embrace. We call it dark matter, not because it is dark like the night, but because it gives off no light at all. It neither glows nor reflects. It is utterly transparent, passing through ordinary matter like a ghost. And yet, this ghostly presence is everywhere, outnumbering the familiar matter that makes up stars, planets, and people. In the grand scheme, dark matter is the hidden scaffolding on which the visible universe is built. We first realized this mysterious matter must exist when we looked at the way galaxies move. Imagine observing a majestic spiral galaxy, millions of stars spinning in a cosmic dance. The outer stars are moving so fast that, by rights, they should be flung off into space. Yet they remain bound, as if an unseen hand is holding them in its grasp. That hand is the gravity of dark matter. Though invisible, its pull is very real. Similarly, clusters of galaxies seem to contain far more mass than what we can see shining. Something unseen is adding to their weight, providing the glue that keeps these vast families of galaxies from drifting apart. Scientists have mapped this hidden matter by observing how its gravity bends light from distant stars and galaxies. In some regions of the sky, we see the light of faraway objects distorted and magnified, as though passing through an invisible lens. These cosmic mirages reveal the presence of massive concentrations of dark matter, lurking in halos around galaxies and threading between them. Through such observations, a picture emerges of a universe where most of the mass is invisible. Like an architect working behind a curtain, dark matter shaped the galaxies and clusters we see today, helping them form by its gravity, even though it itself remains in the shadows. What could this elusive substance be? That question remains one of the greatest unsolved puzzles. We know what it is not. It's not made of the same atoms that build us and the world we touch. All the everyday matter, the stars, the gas, the dust, everything we can detect with telescopes, amounts to only a small fraction of the total mass of the universe. Dark matter accounts for much more, yet it interacts so weakly with normal matter that it might pass right through a planet without a single collision. Scientists have imagined new kinds of particles that might make up dark matter, with names like WIMPs or axions, and built sensitive experiments deep underground to try to catch a glimpse of them. So far, these efforts have only deepened the mystery. Dark matter continues to elude our direct detection. There is a profound stillness to dark matter's role in the cosmos. It doesn't shine or burn or crackle with energy. Instead, it gently tugs with gravity, guiding the formation of galaxies quietly over billions of years. It's like a silent partner in the cosmic dance, always present, but never stepping into the spotlight. We sense it through its influence, much as one might sense a faint breeze by the rustling of leaves, even if the wind itself is invisible. In that way, Dark matter reminds us that not everything real can be seen. Some truths of the universe reveal themselves only indirectly, through subtle effects. As we float in our thoughts amid the vast structures of galaxies, we acknowledge this invisible mass with wonder. It surrounds us even now, enveloping our own Milky Way in a great halo that extends well beyond the visible stars. We drift through it without feeling a thing, yet its gravity is what allowed our sun and planet to come together in the first place. Dark matter's silent presence has been with the universe from nearly the very beginning, shaping the cosmic web like hidden tendrils. And while it remains an enigma, it is comforting in a strange way, a reminder that there is more to reality than meets the eye, that the cosmos still holds secrets close. Our journey now carries us from this unseen form of matter to another kind of mystery, one born not of matter at all, but of gravity in its most extreme form. We turn our attention to places where gravity reigns supreme, where even light cannot escape. We are drawn toward the darkness of black holes, the gravity we cannot see. There are regions in space where gravity is so intense that nothing, not even the fastest light, can escape its grip. These are black holes, perhaps the most eerie and mysterious objects in the universe. They are often described as holes because anything that ventures too close falls in, seemingly vanishing from our observable universe. But a black hole is not a hole in the usual sense. It is a place where a huge amount of mass is concentrated into a very small area. The result is a gravitational trap so strong that once anything crosses a certain boundary, called the event horizon, it is lost to us forever, hidden from sight. Imagine a star much larger than our sun, burning brightly for millions of years. In its old age, it exhausts its fuel and collapses under its own weight. If it is massive enough, it continues collapsing until all its matter is crushed into an incredibly dense point. This point is the heart of a black hole, a singularity, where density and gravity are beyond anything we can fathom. The star's light goes out, and in its place remains a sphere of darkness. If you were to approach this dark sphere, you wouldn't see the singularity itself, only the boundary around it, where light can no longer climb out. Cross that invisible line, and there is no return. Black holes are truly gravity made manifest, yet we cannot directly see them. We infer their presence by their powerful effects on the surroundings. We see stars orbiting frantically around empty regions of space, moving as if whipped around by an invisible giant. In the center of our own Milky Way galaxy, a cluster of stars whirl in circles, betraying the location of a supermassive black hole millions of times heavier than the sun. Occasionally, a cloud of gas or a star wanders too close and gets snared, spiraling into the darkness. As it does, it heats up and glows fiercely just before it disappears, allowing us a fleeting glimpse of the black hole's edge by the light of doomed matter. It is in these moments that the silhouette of a black hole can be seen, as a dark, round shadow against a bright background of swirling gas. A sight humanity has only managed to capture in recent years with our most sensitive telescopes. The mystery of black holes runs deep. We can describe how they form and how they affect their environment. But what lies inside, beyond that event horizon, remains unknown. Our laws of physics break down when we try to describe the singularity at a black hole's core. It is as if the universe keeps this one secret under lock and key. Does time itself come to an end in there? Does matter get destroyed or transformed? We don't yet know. There is also a puzzle known as the information paradox. When something falls in, is all the information about its existence lost forever? Quantum physics suggests information can never be completely destroyed, leading to a profound riddle about how black holes manage what falls into them. Despite their ferocity, black holes can be surprisingly gentle from afar, and even useful. They act as cosmic anchors, with many galaxies harboring those supermassive black holes in their cores. These dark giants may have played a role in shaping galaxies, regulating the birth of stars by their powerful gravitational influence and occasional outbursts of energy. Without them, the cosmos might look very different. In another sense, black holes have become tools for discovery. When black holes collide with each other, the fabric of space itself ripples. We cannot see these gravitational waves with our eyes, but we can listen to them with special instruments on Earth. In recent years, scientists have heard the faint, distant murmurs of black holes merging, a soft chirp in the darkness that confirmed Einstein's century-old predictions. It is a reminder that even in silence, the universe has its subtle ways of communicating. Floating near a black hole's domain in our imagination, we feel both fear and fascination. It is a place of ultimate darkness, but also a crucible where the boundaries of science are tested. Black holes compel us to confront the extreme nature of reality, where space and time themselves can twist into knots. They show us how much we still have to learn. And just as we begin to grasp one mystery, our journey carries us onward to a larger canvas. From the depths of these gravitational abysses to the grand design they are a part of. Ahead lies the vast architecture of the cosmos, the immense structure that all these pieces, stars, galaxies, dark matter, and black holes, help to build. From the smallest of black holes, we now pull back our view and gaze at the universe on its grandest scales. What we see is a breathtaking cosmic architecture, an immense web of galaxies stretching across space. If we could rise high above our galaxy and keep going further and further out, eventually we would see that galaxies are not scattered randomly. They gather together in clusters and chains, interconnected by filaments of matter that span millions upon millions of light years. In between these strands lie enormous voids, vast regions of nearly empty space where galaxies are scarce. Together, this forms the cosmic web, the large-scale structure of the universe. This architecture was built over billions of years, guided by gravity and the foundation of dark matter laid down in the early cosmos. Those tiny fluctuations born in the era of inflation grew into strands and clusters under the influence of dark matter's pull. Galaxies took root, like glittering jewels, along invisible cosmic threads. Over time, islands of galaxies drew together into larger continents of clusters, and those aligned into immense walls and filaments. Our own Milky Way is part of this tapestry, residing in a small group of galaxies, which in turn lies on the outskirts of a cluster known as the Virgo cluster, which is itself one node in a greater lattice, extending as far as we can observe. It is astonishing to consider the scale of these structures. One filament of galaxies can stretch hundreds of millions of light years, end to end. Clusters at their intersections can contain thousands of galaxies. There are cosmic superstructures, such as gigantic walls of galaxies and enormous superclusters that defy easy explanation. Some span more than 1 billion light years across. They are so large that our minds struggle to picture them, and our theories strain to account for how such vast arrangements came to be in the time since the universe was born. It's as if we are ants trying to map the layout of a giant cathedral by touch alone, only gradually realizing the true extent of the edifice around us. When we look at maps of the universe compiled by astronomers, dots of light representing galaxies line up into filaments and clusters amid dark voids, resembling a cosmic spider's web or the neurons of a colossal brain. There is a remarkable order in this arrangement, patterns created by the simple rule of gravity acting over unimaginable distances and times. And yet, even in this order, there are hints of anomalies. One corner of the sky may show an especially dense clumping of galaxies, another, an unusually barren void. We have given names to some of these extreme structures and gaps. They intrigue scientists because, while the broad strokes of the cosmic web make sense to us, these outliers raise questions. Did some regions of the universe evolve differently? Or do these giant structures point to new physics or events in the early cosmos that we have yet to understand? Drifting among these colossal filaments in our mind's eye, we feel a sense of grand design, tempered by the recognition of our own smallness. We find beauty in the vast interconnectedness, as well as humility in how much we have left to discover. The cosmic web connects everything, including us, in a vast network. It tells a story of matter drawing together out of the void, yet it also leaves us with puzzles etched into its very structure. As we marvel at this cosmic architecture, we also note the questions it poses, those patterns in the layout of galaxies that still lack answers. It is to these puzzling patterns and lingering mysteries that our journey now turns. Our exploration of the cosmic structure has revealed a grand design, yet within that design lie peculiar clues that something more may be at play. Subtle patterns and anomalies have emerged that continue to baffle scientists, inviting more questions than answers. These are the oddities that stand out against the otherwise smooth and expected tapestry of the universe. They are like whispers from the cosmos, hinting that our current understanding, as vast as it is, might still be incomplete. One such mystery is written in the very afterglow of the Big Bang. The cosmic microwave background, a faint light bathing the universe, is mostly uniform, but not perfectly so. Upon this canvas of ancient light, astronomers have found unusual features. In one region of the sky, there is an especially cold spot, larger and cooler than what standard models predict. Its size and temperature deviations have led to much speculation. Could it be the imprint of a gigantic supervoid in that direction, an area of space with far less matter than usual? Or might it hint at something even stranger, like a brush with another universe beyond our own? For now, it remains an open question, a cold anomaly in the heat map of creation. Another puzzle lies in the distribution of galaxies themselves. We know they form filaments and clusters, but occasionally we see structures so gigantic they challenge our theories. Astronomers have identified groupings of quasars and galaxies forming colossal alignments and walls across billions of light years. These megastructures are difficult to reconcile with how matter clumps together over the 14 billion years since the Big Bang. There simply shouldn't have been enough time for gravity to assemble objects so immense. When one such immense wall of galaxies was discovered, stretching in a way that seemed to defy the expected limits, it sent a ripple of excitement and doubt through the scientific community. Was it a statistical fluke, a chance alignment of smaller structures? Or does it point to new physics or initial conditions that we have yet to understand? Such patterns tease us with the possibility that the universe's early days might have had surprises we have not yet unraveled. There are even hints of large-scale motions that are hard to explain. Imagine entire clusters of galaxies, each cluster containing hundreds or thousands of galaxies, all streaming subtly in the same direction, as if drawn by a gravitational force beyond our sight. This phenomenon, sometimes called the dark flow, suggested that vast regions of the universe might be moving towards something hidden beyond the visible horizon. If true, it raises profound questions. What might lie outside the observable universe that could tug on such massive scales? Recent studies debate the very existence of this dark flow, and some say it might fade with better data. But the mere hint of it reminds us how much of the cosmos lies outside our grasp, possibly influencing our universe in ways we are only beginning to suspect. These patterns without answers keep cosmologists awake at night and inspire them by day. Each anomaly is a gentle nudge that perhaps our cosmic story has chapters we haven't yet read. For all our breakthroughs in understanding, these mysteries are a humbling reminder of the unknown. They provoke creativity and caution in equal measure. We must consider possibilities that once seemed like science fiction, even as we double-check that our instruments and analyses aren't misleading us. The universe has no obligation to make perfect sense to human minds. Occasionally, it presents what looks like contradictions, which may in time lead to deeper truths. As we ponder these unresolved cosmic riddles, there is a feeling of standing on the shoreline of a vast ocean, with dark and uncharted waters ahead. We have mapped the stars and galaxies like familiar constellations on the horizon. Yet beyond them, hints of new lands remain out of reach. It is at this boundary, this edge of discovery, that we now pause. We gather our thoughts and let the profound silence of the cosmos wash over us, preparing ourselves for whatever revelations may come next on our journey. We have travelled vast distances in our imagination, from the dawn of time to the far reaches of the cosmic web. Along the way, we encountered mysteries that challenged the limits of our understanding. Now, we find ourselves on the very edge of what is known, a tranquil pause before the next chapter of discovery. Here, at this quiet frontier, the cosmos stretches out before us in silent wonder, and we allow ourselves a moment of rest. In the stillness of this pause, we reflect on the profound journey so far. We stood beneath the infinite night sky and felt the overwhelming vastness of the universe. We witnessed the birth of everything in a flash of light and the long darkness that followed. We pondered the swift, inflationary breath that set the stage, and the unseen dark matter that gently holds the galaxies together. We ventured close to the abyss of black holes and pulled back to marvel at the grand cosmic web. Each step brought new questions, and with each question, a deeper appreciation for the universe's secrets. Now we drift at the boundary between the known and the unknown. It is a peaceful place, tinged with a sense of anticipation. Ahead of us lie more enigmas, questions still unanswered, and the promise of further exploration. But for this moment, it is enough to simply float here in the silence of space, heart and mind open to the beauty of it all. The stars in the distance shine calmly, as they have for eons, unconcerned by our curiosity, yet inspiring it all the same. We breathe in the cosmic perspective we have gained. The universe is vast and mysterious, and we are small, but we are also a part of this grand story. In the quiet, we feel a connection to the stardust from which we came, and to the endless sky that surrounds us. There is comfort in not knowing everything, in understanding that some mysteries will beckon us onward. It means the story isn't over. that there is more to seek and discover when we are ready. As we linger at this edge of discovery, we allow the serenity of the unknown to wash over us. Here, wrapped in starlight and possibility, we close our eyes and simply listen to the gentle hum of the cosmos. In this gentle darkness, with the wonders we've seen still dancing in our thoughts, we find peace. Our journey will continue, but for now, we rest, cradled by the infinite night. We drift onward through the cosmic night. In the silent darkness between distant galaxies, something subtle and profound is at work. The universe expands, and it has been expanding since its fiery birth. Yet this expansion holds a deep mystery. It is not slowing down as once imagined, but accelerating. Galaxies drift ever farther apart, propelled by an unseen influence that permeates all of space. Astronomers long believed that gravity would gradually break the expansion of the cosmos. It seemed intuitive that the mutual pull of galaxies on each other might one day slow and perhaps even reverse the cosmic spread. But to their astonishment, late 20th century observations revealed the opposite. Distant supernovae, exploding stars used as cosmic beacons, appeared dimmer than expected, indicating they were farther away than their velocity alone could explain, a sign that the expansion of the universe has been speeding up. The scientific world was astonished. At first, many astronomers hesitated to believe what their data suggested. Could the universe truly be accelerating apart? One by one, distant supernova observations painted the same surprising picture. It was as if a subtle cosmic hand were pushing galaxies outward with ever-increasing strength. Over a few short years, skepticism gave way to awe as evidence mounted, and a new understanding began to take shape. This discovery forced a reimagining of cosmic history. For billions of years after the Big Bang, gravity had been slowing the expansion, as everyone expected. But around 5 billion years ago, a tipping point was reached. An unknown force overtook gravity's gradual braking and began to speed up the expansion instead. The universe, it turned out, had entered a new era in which this mysterious influence dominated. Today, by the estimates of cosmologists, this dark energy accounts for nearly 70% of all the energy in the cosmos, making it the single largest component of existence. It is everywhere, yet it reveals itself only through the acceleration of space. Scientists gave this enigmatic force a name: dark energy. Dark energy is not something we can see or touch, yet it seems to fill the fabric of the cosmos like an invisible mist. Rather than pulling things together as gravity does, it pushes space outward. It behaves as if the vacuum of space itself contains a gentle pressure, a push that grows stronger as space expands, driving galaxies apart at an ever-increasing pace. We find ourselves faced with a universe dominated by this baffling phenomenon. By current estimates, dark energy makes up most of the cosmos in terms of energy content, far outweighing the mass of all galaxies, stars, and nebulae. It is as though an immense, unseen reservoir of energy is woven into the very structure of space. And yet, despite its overwhelming influence, we understand next to nothing about what dark energy actually is. The term dark reflects our ignorance. It is a placeholder for a cause we have yet to identify. Still, we feel its effects with each new measurement of distant galaxies. With every passing moment, the space between clusters of galaxies stretches wider. Over billions of years to come, this expansion will carry galaxies beyond each other's reach. deepening the vast gulfs of emptiness. It raises profound questions. Why is the universe's expansion accelerating instead of slowing down? What is this mysterious energy that counteracts gravity's pull? These questions drift through the minds of cosmologists as they gaze into the night sky, wondering at the force that propels the universe's growth. Our journey now turns to the puzzle at the heart of this cosmic acceleration. We have given a name, dark energy, to the unknown driver of the universe's runaway expansion. But a name is not an explanation. To truly understand, we must ask, why does the cosmos accelerate at all? Picture yourself floating in the vastness between galaxies. Around you, the darkness is quiet and still. In the distance, clusters of galaxies drift apart like tiny islands carried by a slow cosmic current. Over eons, you would see them inch away, the space between growing larger and darker. It is as though the universe is breathing out, gently but relentlessly, and you are witnessing that silent expansion from a front row seat. Why indeed does the cosmos accelerate? This question remains at the forefront of modern cosmology, and the answers are elusive. We know the effect, space expanding faster and faster, but not the cause. In trying to understand it, scientists ponder whether something special is built into the fabric of space itself. Perhaps empty space is not truly empty, but endowed with its own energy that gently repels, causing space to swell ever more rapidly. Over a century ago, even Albert Einstein toyed with the idea that space might hold such an energy. He introduced a cosmological constant into his equations, a kind of mathematical fix, suggesting a static balance between gravity and an inherent outward push. Later, when the universe's expansion was discovered, he abandoned the concept, calling it his greatest blunder. Yet decades on, the notion resurfaced. Maybe this constant was real after all, manifesting as the dark energy now driving the acceleration. In hindsight, Einstein's once speculative idea seems prescient. Empty space behaving as if it has a subtle springiness, an inbuilt urge to expand. The idea that empty space could contain energy may seem counterintuitive, but physics hints at such a possibility. Even what we call a vacuum is not truly nothing. Quantum theory tells us it seethes with tiny fluctuations. Particles flicker into existence and annihilate in a ceaseless quantum dance. This invisible activity, though incredibly subtle, might imbue space with a small amount of energy. If so, every bit of space contributes a touch of outward pressure. Spread across the cosmic vastness, this gentle pressure could add up to the force driving the acceleration. Dark energy, in this view, could be the collective effect of countless virtual particles and fields in empty space, a quiet energy of the vacuum itself. Even so, a simple constant energy filling space is only one possible explanation. Some researchers wonder if dark energy might change over time, slowly strengthening or weakening as the universe evolves. They imagine an exotic field permeating space, one that waxes and wanes over cosmic history. If this is true, then the future of the cosmos could hold surprises. The acceleration might speed up even more dramatically, or, conversely, fade away in the far distant future. So far, however, observations hint that dark energy acts consistently, more like a steady push than a wild variable force. Scientists are actively searching for any signs that dark energy might be changing. By observing the light of distant supernovae and mapping the expansion at different epochs, they hope to see if dark energy was stronger or weaker in the past. Any variation could mean that dark energy is not a constant at all, but something dynamic, perhaps a slowly rolling field that evolves over time. So far, however, the data suggests no significant change, reinforcing the notion of a steady influence. If dark energy does vary, its effects are too subtle for us to detect with current instruments, keeping this question open for future discoveries. Another possibility is that our understanding of gravity itself needs revision. The laws of physics, as we know them, have been extraordinarily successful, yet they might not tell the whole story on the largest scales. Could it be that gravity behaves a little differently across the vast distances between galaxies, in a way that mimics the effect of dark energy? A few bold theories propose modifications to gravity's rulebook, a tweak in the cosmic code that would naturally produce acceleration. But these ideas too remain unconfirmed, and for now, dark energy is the simplest story that fits the facts. The implications of an ever-expanding universe are profound. A once popular theory envisioned a big crunch, where gravity would eventually halt the expansion and pull everything back into a fiery collapse. Now, with dark energy in control, that outcome seems nearly impossible. Instead, the distant future looks lonely. Galaxies not bound to our own will slip farther and farther away until their light no longer reaches us. In trillions of years, an observer in our galaxy, or its merged descendants, might find the night sky empty of all but the faint glow of stars within our local island of space. The cosmos would continue to expand silently, each cluster of galaxies marooned in darkness. Even without dark energy growing stronger, such a fate is a quiet extinguishing, a big freeze, where the universe cools as stars burn out and new stars no longer form. Over incomprehensibly long timescales, even black holes might evaporate, leaving a thin haze of fundamental particles drifting in endless night. Yet if dark energy were to grow in strength, a scenario that remains speculative, the cosmos could meet an even stranger end. In this hypothetical Big Rip, the repulsive force would increase without bound, eventually overcoming all other forces. In the final moments, galaxies would be torn apart, then star systems, and finally even atoms ripped asunder as space itself dilates catastrophically. Such an ending, if it were to occur, lies far beyond billions of years in the future, in an epoch so distant that it almost loses meaning in human terms. For now, our universe is in a balance of motion, a delicate tug-of-war between gravity pulling matter together and dark energy pushing space outward. This balance determines how space itself is shaped and how it will evolve. To explore further, we must step back and consider a fundamental question about the cosmos. What is the shape of the universe that is expanding so swiftly around us? In seeking answers, we turn our gaze to the very geometry of reality, pondering the shape of infinity. What is the shape of space on the grandest scale? When we think of shapes, we imagine edges and boundaries. But the universe seems to defy such simple notions. Peering into the depths of the cosmos, we find no sign of an outer wall or a center from which everything radiates. Instead, space appears to stretch uniformly in all directions. If the cosmos has a shape, it might be one without edges, curving in on itself or extending infinitely, a geometry difficult to picture, yet hinted at by subtle clues in the light of ancient stars. One way to imagine it is to use analogies. Think of the two-dimensional surface of a balloon. It has no edges, yet it is finite in area. A creature confined to that surface could wander endlessly in any direction and never find a boundary, eventually looping back around. Some scientists have wondered if our three-dimensional space could be similar, perhaps curving through a higher dimension to close back on itself. If so, the universe would be finite in volume, but without any edge or outside, much like how the balloon's surface has no edge for the ant walking upon it. Alternatively, space might be truly infinite, like an endless flat expanse. In this case, if you travel forward in a straight line, you would never return to your starting point. You could go on forever, always finding more stars and galaxies, though beyond a point they might start to repeat in their arrangements, as infinity allows endless possibilities. This concept of an infinite universe is daunting. Our minds struggle with the idea of something that has no end and no boundary. Yet current observations of the cosmos suggest that it is astonishingly close to geometrically flat, which is the kind of shape that could extend without limit. Measurements of ancient light, the cosmic microwave background that bathes the universe, act like a massive cosmic surveyor's tool. From these observations, scientists have found that space is not visibly curved on the largest scales we can see. If there is curvature at all, it is so slight that our whole observable universe is just a tiny patch on a much larger, gently curved surface. In practical terms, this means the universe, as far as we know, is effectively flat, aligning with the possibility of infinite extent. Still, we cannot be sure what lies beyond the horizon of what we can observe. The universe could be far larger than what we see, or it could wrap around in ways that our instruments have yet to detect. To determine the universe's shape, scientists look to the sky for clues. The cosmic microwave background, the faint afterglow of the Big Bang, serves as a giant canvas for geometry. Tiny variations in this background light form patterns that depend on the curvature of space. By analyzing these patterns, cosmologists have found that space is very nearly flat, meaning that, as far as we can see, parallel light rays continue without converging or diverging. If the universe does curve into a closed sphere or open saddle, the radius of that curvature must be enormous, far beyond the observable portion. In other words, our cosmic horizon is not showing any obvious warping of space on the largest scales. Intriguingly, a perfectly flat universe can still be finite if space is connected in unusual ways. Much like a video game world, where traveling off one edge of the map brings you back from the other side. Some models suggest the cosmos might wrap around on itself in complex three-dimensional loops. If that were true, we might see ghostly repeats of distant galaxies or patterns of light echoing across the sky, essentially glimpses of the same object in different directions. Astronomers have searched the cosmic microwave background for such repeating circles or unusual alignments that could hint at a finite, wrapped-around universe. So far, they have found no convincing evidence of this. The observations are consistent with a space that, whether truly infinite or merely vast beyond comprehension, has no detectable boundary or repetition within our horizon. The shape of space ties into what the universe contains. A cosmos heavy with matter might curve into a cosmic sphere. One with too little could open outward like a saddle. But our universe sits in a balance, seeming to tip toward flatness. Inflationary theory, the idea that in its first moments the universe expanded incredibly fast, offers one explanation by smoothing out any curvature. Whatever the reason, the lack of detectable curvature leaves us with the tantalizing prospect that space stretches on and on. We are left with profound implications. If space truly goes on forever, then infinity becomes part of our reality. If it curves and closes, the universe is still boundless to us, yet finite in total size. Each possibility is awe-inspiring in its own way. And so, we arrive at a fundamental question that naturally arises from these considerations. Is the universe finite or endless? Imagine embarking on a journey through space, setting a course straight ahead and never turning. You travel past stars and galaxies for millions of years. Behind you, the Milky Way fades into a pale glimmer, and ahead, new clusters emerge. But still, there is no end in sight. If the universe is infinite, you could continue this voyage forever, always discovering new realms. If it is curved and finite, you might eventually find yourself arriving back where you began, having crossed the cosmos without ever finding a boundary. The very thought of such a voyage stretches the mind, highlighting how different the universe is from our everyday world. Is the universe finite or endless? It is a question that has tugged at human curiosity for as long as we have gazed at the stars. If the cosmos is finite, then in principle, there is a certain amount of space and a countable number of galaxies and stars within it. If it is infinite, then space stretches on without limit, containing endless galaxies and perhaps infinite repetitions of cosmic patterns. Both possibilities are difficult to grasp, each expanding our minds in different ways. Imagine first that the universe is truly infinite. In an infinite expanse, anything not forbidden by the laws of physics could exist somewhere. The sheer size would be beyond comprehension. Unending chains of galaxies drifting through an endless void. In such a reality, every night sky, on every planet, around every star, would reveal just a tiny, local patch of an immeasurable whole. Our own observable universe, vast as it is, would be merely a small window in an endlessly unfolding panorama. The idea can be both humbling and oddly comforting, suggesting that the cosmos has no bounds and that there will always be more beyond the farthest horizon we can see. An infinite universe carries mind-bending implications. If space truly has no end, then somewhere, far beyond any distance we could fathom, there would be more galaxies and stars continuing endlessly. In an infinite expanse, the sheer numbers defy imagination. Infinite stars, infinite planets, and perhaps even infinite opportunities for things to occur. In such a reality, anything that is physically possible might exist somewhere out there, no matter how far-fetched. There could be regions where galaxies are arranged differently, or even a place, trillions of light years away, where the night sky might look almost like our own, due to chance. These ideas blur the line between science and philosophy, leaving us marveling at how little of the whole we can see. Now imagine instead that the universe, while enormous, is finite. In this scenario, space might curve back on itself in a grand cosmic loop. If you could somehow travel in one direction long enough, you would eventually end up back where you started, even though you never encountered an edge or a wall. The universe would have a definite size, but no one would ever find a boundary or fall off a literal edge. Much like how on Earth one can sail endlessly without finding an end to the ocean. A finite universe is self-contained. Beyond it, there would be no space as we know it. The very concept of outside the universe might be meaningless if space itself is a closed shape, encompassing all that exists. On the other hand, a finite universe that has no boundary is equally challenging to grasp. We are used to every object having an outside or an edge. But if space itself is curved into a closed shape, one could travel indefinitely and never find a wall or an end. It is a self-contained realm. Asking what lies outside such a universe is like asking what lies north of the North Pole. It's a question that stretches beyond our normal frame of reference. For us living inside it, the universe would feel endless, even if it wraps around on itself. Whether finite or infinite, the cosmos offers no easy vantage point for us to view it from the outside. We must infer its nature from within, piecing together clues and trusting our measurements. Whether finite or infinite, the universe hides its true scale behind a veil we cannot yet pierce. We are limited by the observable horizon, the distance light has travelled since the Big Bang, which defines the sphere of space we can see. Beyond that horizon, there may be vastly more universe that we will never directly observe. It could extend forever or fold unto itself. From our vantage point, both scenarios look almost the same. Astronomers search for subtle clues, perhaps patterns in distant light or shapes in cosmic maps that might hint at a finite topology. So far, the evidence does not show any repetitions or boundaries within the observable patch, leaving open the tantalizing possibility that space truly goes on indefinitely. This profound uncertainty about the universe's extent leads us to an even more astonishing possibility. What if the question itself is too limited? Perhaps the cosmos we live in, whether infinite or finite, is just one of many. Could there be other universes, separate realms, with their own vast expanses of space and time? The idea sounds like pure imagination, yet modern science has begun to consider seriously the existence of a multiverse, a grander reality in which our universe is but a single chapter. Our journey now ventures beyond our universe, into the speculative realm of multiverses and hidden realms. An infinite universe can sometimes feel as unfathomable as having countless universes. As we wonder about the limits of our own cosmos, we naturally begin to ask, might there be more than one universe? The possibility of a multiverse takes us even further into the realm of the unknown, challenging the notion that our universe is all there is. Our universe might not be the only universe. As extraordinary as it sounds, modern theories allow for the existence of a multiverse, countless other universes outside, or alongside, our own. Picture our universe as a bubble of spacetime, born in the Big Bang. Now imagine an ocean of other bubbles, each a separate universe with its own stars, galaxies, and perhaps its own laws of physics. In some theories, during the earliest moments of creation, space expanded unimaginably fast, a process called cosmic inflation, and never completely stopped. It could have generated bubble after bubble, each Big Bang spawning a new isolated cosmos. Our entire observable sky would then be just one bubble in a limitless froth of universes. The multiverse idea gained footing partly through the theory of cosmic inflation. In the split second after the Big Bang, our universe is thought to have expanded at an astonishing, exponential rate. If inflation didn't end everywhere at once, then some regions of space could keep inflating while others slowed down. Each region that stops inflating would form a bubble universe, separated from other regions by still inflating space. This process could be eternal. New universes budding off like bubbles in a boiling pot, continually and forever, creating a vast multiverse of disconnected worlds. These other universes are often referred to as hidden realms, because, by their very nature, they would be cut off from us. No light or signal from them can reach us, at least not through the normal channels of space as we understand it. They might be separated by vast stretches of space and time, or even by barriers of physical law. If you could somehow step outside our universe, a thought experiment at the edge of imagination, you might see an endless expanse of these cosmic bubbles, each glimmering faintly with the glow of its own galaxies. They would be like a multitude of lanterns floating in a great dark sea, each illuminating its own space, unaware of the others beyond a dim boundary. We can indulge in a fanciful vision. If you could somehow step outside our universe, what might you see? Perhaps an endless expanse of a higher reality, dotted with luminous bubbles. Each bubble would be a universe, glowing faintly with the light of its countless stars. They might float like lanterns on a cosmic sea, isolated from one another by vast stretches of nothingness or by walls of physics we cannot penetrate. In this imaginary panorama, our own universe would be just one spark among myriad others, a single note in an ever-expanding cosmic symphony. What would these other universes be like? Some might be very similar to ours, with familiar physics and galaxies, simply too far to ever reach. Others could be wildly different, governed by different fundamental constants or forces. Perhaps in one, gravity is far stronger, preventing stars from lasting long. In another, atoms might not form at all. There could be universes with additional dimensions of space or fewer. Universes filled mostly with water-like substance, or universes that flicker in and out of existence in a heartbeat. The multiverse concept allows every possibility to play out somewhere across the grand ensemble of realities. In such a multiverse, each universe might have its own distinct properties. The fundamental constants of nature, things like the strength of gravity or the charges of particles, might differ from one universe to the next. Most universes could be sterile or bizarre, with conditions unsuitable for stars or life. Perhaps only a few, like ours, have just the right balance to form galaxies, planets, and living beings. Some scientists point out that if there are myriad universes, it might not be surprising that we find ourselves in one that is hospitable. We couldn't exist in the others. This reasoning, called the anthropic principle, offers one way to think about why our universe has the characteristics it does, though it doesn't provide a concrete answer. The idea of a multiverse also arises in the realm of quantum physics. Some interpretations suggest that every quantum event, each random flicker in the subatomic world, could spawn new branches of reality. In this view, there may be parallel worlds where outcomes differ. A vast, ever-branching collection of universes formed by the tapestry of chance. While this many worlds picture is tantalizing, these branching universes, if they exist, are of a different character than the cosmic bubbles. They would represent alternate histories, rather than separate external spaces. Both ideas stretch our understanding of existence and challenge us to rethink what we consider reality. For now, the multiverse remains a theoretical landscape, a maze of possibilities with little direct evidence. We cannot yet peer into these other realms or prove their existence, but the mathematics of our best theories invite the speculation. It expands our horizons from one universe to perhaps an infinity of universes, a hierarchy of worlds nestled within an ultimate reality. And in some of these theories, the existence of other universes ties into another profound idea, that they might be lurking in dimensions beyond our own. The concept of extra dimensions offers one way that multiple universes could coexist invisibly. To explore that, we turn to the idea of dimensions beyond the familiar three of space and one of time that we know. We are accustomed to the three dimensions of space that we move through, plus the dimension of time through which we progress. Up and down, left and right, forward and back. These are the directions we know intimately. But what if there are other directions, other dimensions, that we simply cannot perceive? It's a mind-expanding thought, an entire axis of movement or existence beyond the ones we know, hidden from our senses, yet perhaps just as real. To grasp this idea, imagine a tiny world of two-dimensional beings living on a flat sheet of paper. They have length and width, but no concept of height. If you, as a three-dimensional being, were to lift that sheet, they would have no idea their entire world moved in a direction they cannot sense. To them, this third dimension is invisible and inconceivable, yet it exists all around them. Now think of us in our three-dimensional world. We might likewise be unable to perceive an additional spatial dimension that lies beyond our experience. Our universe could be like a vast, flat surface, though three-dimensional from our perspective, embedded in a higher dimensional space. We would be unaware of a fourth spatial direction if one exists, just as those flat beings know nothing of up. Modern physics has indeed entertained the possibility of extra dimensions. In some theories, space might have additional dimensions that are curled up so tiny that we never notice them. For example, string theory, an ambitious framework aiming to unify all forces of nature, suggests that there could be 6 or 7 extra spatial dimensions rolled up at microscopic scales. These dimensions would be so small that even our most powerful instruments cannot detect them directly. Yet they could subtly influence the behavior of fundamental particles and forces. The gravity we feel, for instance, might be leaking into these hidden dimensions, which could explain why gravity is so much weaker than the other forces we observe. Scientists have devised clever experiments to search for evidence of extra dimensions. One approach is to test gravity on very small scales. If there is a hidden dimension, gravity's strength might subtly deviate from expectations at short distances, as some of its influence could be leaking into unseen directions. Researchers have used sensitive torsion balances and other instruments to measure gravitational attraction between objects, just fractions of a millimeter apart. So far, these tests have not detected any anomalies in gravity's behavior. No sign of a fourth spatial dimension up to those scales. Another approach is through high-energy particle experiments. In powerful accelerators, particles are smashed together, and physicists watch for any missing energy or unusual particles that could indicate something slipping away into an extra dimension. To date, nothing definitive has appeared, but these searches can only probe certain size scales and energies. The possibility of extra dimensions is not ruled out. It may simply be that they are too subtle or small for current technology to reveal. Another perspective comes from the idea of a brain world. In this scenario, our whole universe could be a three-dimensional membrane, a brain, floating in a higher dimensional space. All the matter and light we know would be stuck to this brain, unable to leave it, which is why we cannot see anything outside our 3D universe. But gravity, which interacts with the fabric of space itself, might extend a bit into the extra dimensions, providing a possible bridge or hint of their existence. If there are other brains out there, they could be parallel universes, separated from ours not by distance in the usual sense, but by a small gap in an unseen dimension. Perhaps, in some extraordinary way, the multiverse and extra dimensions are linked. Other universes might literally be next door in a higher dimensional sense. We could never reach them by traveling in our normal 3 dimensions. Considering dimensions beyond our own pushes us to the limits of imagination. We cannot see or touch these hypothetical directions, but mathematics allows them, and they offer elegant explanations for some puzzles in physics. Whether or not extra dimensions truly exist, the concept reminds us that reality may have layers and structures we have barely begun to fathom. And this brings us to another thought-provoking idea. Even within the dimensions we know, perhaps the fabric of space hides an intricate structure at scales too small or too large for us to notice. Is there an invisible framework underlying everything, a scaffold or lattice that shapes reality itself? Our journey now turns to that hidden structure, the invisible lattice of reality. It's intriguing to ponder what a higher dimensional perspective might be like. If a fourth spatial dimension exists, a being that could move through it would see our world in a startling new way. They might observe the inside of a closed box without opening it, or take a shortcut from one point to another that seems unconnected in our 3D space. To us, bound to our familiar dimensions, such feats are unimaginable. Yet if extra dimensions are out there, they form a larger framework that our universe is part of, a reminder that our perception may only capture a slice of a richer cosmic reality. On the grandest scales, the universe displays a mysterious pattern, an immense cosmic web stretching across space. Galaxies are not scattered randomly. They collect into clusters and long filaments, threading outward in a vast network. Between these filaments lie enormous voids, regions with far fewer galaxies, like dark hollows between bright strands. The result is a structure that resembles an infinite lattice or sponge, with matter concentrated along the threads and emptiness in between. This is the cosmic web, an invisible lattice of gravity and matter that underlies the visible universe. What forms the backbone of this cosmic web is something we cannot see: dark matter. Though we cannot observe dark matter directly, its gravity betrays its presence. It gathers in clumps and filaments, drawing in ordinary matter, gas and dust that eventually forms stars and galaxies. Over billions of years, these invisible tendrils of dark matter have guided the formation of galaxies, much like unseen scaffolding upon which the visible structures of the universe were built. Astronomers map the cosmic web by looking at galaxies and by measuring how light from distant objects is bent, a subtle gravitational lensing effect caused by invisible strands of dark matter. What emerges from these studies is a remarkable vista, a universe shaped by an unseen lattice, immense in scale. Drifting within this web, a galaxy like our own Milky Way is merely a tiny node at the intersection of filaments. From our earthly perspective, the night sky looks random and scattered. But on the scale of hundreds of millions of light years, order emerges from the darkness. It is humbling to think that our entire galactic neighborhood traces just one thread in this colossal cosmic tapestry. The voids between threads are not entirely empty. They contain tenuous gas and stray galaxies. But compared to the busy intersections, they are vast, lonely expanses. If we could soar far above the cosmic web, the view would be breathtaking. Imagine looking down upon countless galaxies at once. You would see them arranged in filaments and clusters, a glowing lattice against darkness. The great voids would appear as vast black gaps between bright strands of galaxies. Drifting along a filament, you would pass cluster after cluster, each a glittering city of stars, until you reached an enormous void where galaxies are sparse. Crossing that void would feel like traversing a deep ocean trench. Silence, darkness, and the faint light of distant galaxies far behind. Then another filament would emerge ahead, and you'd dive back into the populated cosmic highways of galaxies. Though you cannot see the dark matter directly, its gravitational influence is the architect of this grand design, guiding your path along the invisible scaffold of the universe. You would find this pattern repeating, filament to void to filament, across the cosmos. In its grand and subtle way, The universe's structure reveals itself only through the pull of gravity and the glow of stars, hinting at the underlying dark scaffold that holds it all together. There are fundamental questions raised by the existence of this structure. What exactly is the dark matter composing these filaments? Why did matter arrange itself in this particular pattern? Might there be an even deeper level of structure beneath what we have observed? Turning from the immense to the minuscule, some scientists suspect that space itself may be woven with an invisible lattice at the smallest scales. While the cosmic web is a structure of galaxies across billions of light years, there could be a very different kind of lattice operating at a scale trillions of times smaller than an atom. Quantum physics hints that the fabric of space-time might not be smooth if you zoom in far enough. Instead, it could be frothy or granular, what some call quantum foam. At the Planck scale, distances and times are so minute that our usual understanding of space breaks down. It is possible that space is not infinitely divisible, but instead made of discrete units, the way matter is composed of atoms. These units would form a grid so fine that to us it appears continuous. This hypothetical microscopic lattice would be the invisible underpinning of reality, a hidden order beneath the apparent continuum of space and time. We have not yet detected such a fundamental lattice. Our current instruments are far from probing those Planck-length scales. Still, the idea inspires wonder. If true, it means that there is a limit to how finely we can divide space and time, a built-in pixelation of reality itself. In a way, it would imply the universe has a kind of hidden code or blueprint underlying everything. Coupled with the cosmic web on the largest scale, it suggests that from the very big to the very small, the cosmos has a structure that is largely invisible to us, guiding the form and behavior of what we do see. These concepts remind us of how much remains unknown. The dark matter lattice of the cosmic web is mapped yet still unexplained. We do not know what dark matter truly is, or why it exists. The quantum lattice of space, if it exists at all, lies entirely beyond our reach for now. The universe shows us patterns and hints of a grand design, but the deeper mechanisms remain elusive. As we ponder these mysteries, we find ourselves compiling a growing list of unanswered questions that thread through the very fabric of space. It is to those unanswered questions that we now gently turn, reflecting on what we have yet to learn. Gazing at the tapestry of cosmic mysteries we have explored, one thing becomes clear. There is far more that we do not know than we actually understand. The fabric of space is embroidered with unanswered questions, each thread representing a profound unknown. We have identified phenomena like dark energy, but we still cannot fathom what it truly is or why it exists. We feel its push in the accelerating expansion of the universe, yet its nature remains as shadowy as the depths of intergalactic space. Consider also dark matter, the hidden mass forming the cosmic web's scaffolding. For decades, we have observed its gravitational imprint, guiding stars and bending light, yet not a single dark matter particle has been directly seen or captured. What is this elusive substance that outweighs all the visible stars and galaxies? Is it a particle, a field, or something entirely unimagined? Until we detect it and understand its properties, the composition of most of the matter in the universe remains an open question, floating in the darkness. We ponder the shape and extent of the universe itself. Is space infinite, carrying on without end? Or is it closed, curving back on itself in a way we cannot easily visualize? Our best measurements say the universe is remarkably flat, nudging us to think it might be endless, yet we cannot be certain. If the cosmos is finite, what lies beyond its boundaries, or is beyond even a meaningful concept if space itself ends? And if it is infinite, how did infinity come to be? And what does it mean for there to be an endless expanse of reality? These questions linger, unanswered, at the fringes of cosmology. Then there is the tantalizing possibility of other universes. Are we alone in an ultimate sense? Or is our universe just one of many bubbles afloat in a larger multiverse? If other universes exist, we may never see them. Yet their existence could explain aspects of our own universe. Perhaps the fortunate set of physical laws that allow galaxies and life to exist here. It remains a speculation, a question that stretches science to its philosophical edges. How far does reality extend beyond what we can observe? Likewise, we wrestle with the idea of dimensions and the fundamental nature of space-time. Could there be hidden dimensions curled up beyond our perception? And if so, why can't we access them? Or might space at its smallest scale be quantized, broken into tiny pieces by an underlying lattice or grid? We search for a theory that unites the physics of the very large, gravity and cosmic expansion, with the physics of the very small, quantum mechanics. This quest for a unified understanding, a theory of quantum gravity, is perhaps the ultimate unanswered question about the fabric of space and time. Solving it might reveal whether space is smooth or pixelated, and how the universe began in that first incandescent moment of the Big Bang. Even the origin and fate of the universe remain shrouded in mystery. We have theories of how the universe evolved from fractions of a second after the Big Bang to now. But the moment of creation itself, and whatever preceded it, remains out of reach. Why did the Big Bang happen at all? Was it the beginning of time, or a transition from an earlier state? And looking forward, we can predict various scenarios for the cosmos's end. Eternal expansion into a cold void, or a ripping apart of space if dark energy grows stronger. But we cannot say for sure which destiny awaits us, or if something entirely unforeseen will alter that fate. Each question seems to lead to another, in an endless cascade. Yet rather than leaving us in despair, this uncertainty instills a sense of wonder. It is a reminder that the universe, in all its vastness, is not a puzzle to be quickly solved, but a profound mystery to gently unfold. We stand on the shoreline of the cosmic ocean, knowing there are deep waters ahead that we have yet to explore. With every advance in technology and thought, we answer one question only to uncover new ones, maintaining that delicate balance between knowledge and mystery. In the silence of space, these unanswered questions quietly beckon us. They fuel our curiosity and drive our quest to understand. We take comfort in the not knowing, for it means there is so much more to discover, and the story of the cosmos is far from over. And so, as we reflect on these open mysteries, we find ourselves ever so slowly drifting toward the next chapter of this cosmic journey, a chapter that remains unwritten, waiting in the unknown. Standing on the shores of what is known, we peer into the cosmic ocean and sense the infinite questions that lie beyond. The night sky above is full of gentle mysteries, each star and galaxy a beacon of something we have yet to fully understand. As you take a slow breath and gaze upward, you can feel both the immensity of what's out there and the stillness of not knowing. In that quiet, there is a peaceful acceptance that some answers await far in the future, and some might always elude us. We continue to drift forward, held aloft by curiosity and wonder, into the unknown expanse where new discoveries shimmer just out of reach. We drift now, in a quiet reverie, through the cosmic darkness. All around, the stars glimmer softly, each a distant mystery we have touched upon in thought. The hush of space feels comforting, like a gentle blanket of night, enveloping us as we float. In this peaceful moment, we carry with us all the wonders we have encountered, not as burdens, but as light companions on our journey. The unknown no longer feels like an abyss to fear. It is a calm sea of possibilities, inviting us to sail further. Our journey in this part has been like a slow voyage through a gallery of cosmic mysteries. We wandered among ideas vast and subtle, the invisible force that pushes the universe apart, the shape of space stretching to infinity, the tantalizing maybe of other universes unseen, the possibility of dimensions curled beyond perception, and the hidden scaffolding that underlies reality. Each topic rose before us like a gentle wave, and we rode it, unhurried, absorbing the wonder it offered. Now, as those waves subside into memory, we find ourselves gliding onward, our course guided by curiosity and awe. There is a serenity in recognizing that we do not have all the answers. The cosmos holds its secrets tightly, yet it shares enough of its beauty to captivate us. We can float in that balance between knowing and not knowing, and find peace. In the grand scheme, our questions are small beacons, like stars themselves, points of light that give us direction in the vast darkness. We follow them, one by one, never running, only drifting, patient and open to whatever comes. As we continue this gentle drift into the unknown, the distinctions between what we have learned and what we have yet to learn blur into a continuum of exploration. We are simply here, present in the cosmic ocean, our minds quiet but alert, our hearts steady. The mysteries ahead do not press on us. They simply shine, waiting for us to arrive in our own time. In the distance, one can almost sense the faint glow of new revelations just over the horizon of understanding. For now, we reside in the space between stars and questions, content to float and feel the subtle currents of the universe around us. The journey itself, this calm exploration of existence, is as meaningful as any destination. And so we drift, gently and without fear, deeper into the cosmic night. A tender voyage through darkness, lit softly by the promise of discovery. The endless expanse stretches quietly before us, and we move onward, carried by wonder into whatever mysteries lie ahead. In the silent expanse of our journey, we now drift into the deepest mystery of all, time itself. We sense time intimately in the rhythm of our breath and the turning of earth, yet its true nature eludes our grasp. For ages, people marked time by the cycle of seasons and stars, believing it flowed like a great river. Modern physics, however, offers a startling insight. Time might not flow at all. In Einstein's view, past and future exist together, and time simply is. We find ourselves wondering then why we feel carried along, moment by moment, if physics sees no cosmic clock's current. This gentle paradox beckons us to explore how time can feel so real and yet be so mysterious, inviting us deeper into its enigma. It helps to remember how our understanding of time has changed. In the 17th century, Isaac Newton imagined time as absolute and unchanging, flowing equably without regard to anything external, he said. To Newton, time was like a grand stage on which events unfold in orderly sequence, the same universal time for one and all. That idea endured for centuries, comforting in its certainty. But in the early 1900s, Albert Einstein shattered this certainty. He merged space and time into a single fabric called spacetime, revealing that my time and your time need not agree. A moving clock can tick slower than a stationary one, a fact we usually notice only with precise instruments. For instance, a clock on a jet airplane registers a few microseconds less than one on the ground. Gravity, too, can make time malleable. A clock deep in a gravitational field, say at sea level, runs a bit slower than one on a mountaintop or in space. There is no single universal time at all. Each of us carries our own little stream of time, affected by how fast we move and where we are. Reality's stage is not rigid. It subtly stretches and shrinks time's intervals as objects move or gravity bends space around them. Imagine floating near a black hole, one of nature's most extreme gravitational wells. From afar, we would see your movement slow down as you neared that dark abyss. Every heartbeat and every gesture would appear to us to stretch out longer and longer. In fact, as you approach the black hole's boundary, the event horizon, our instruments would show your clock ticking ever more slowly, as if time itself were freezing. Astronomers once called such objects frozen stars, because anything falling toward them seemed to slow to a standstill at the edge. To you, on your perilous journey, time would feel normal, seconds passing at their usual pace. But you could look outward and see the entire universe speeding by in a blur of eons. This isn't science fiction, but a consequence of Einstein's general relativity. In principle, if you hovered safely near a black hole for just an hour, you might return to find years or centuries have gone by in the outside universe. The thought is breathtaking. Gravity can pull on time, stretching 1 hour into many years. Black holes, with their immense gravity, show us time's astonishing flexibility. They teach us that time is woven into the fabric of space, and under extreme conditions that fabric can be pulled almost to breaking point, a gentle ticking slowing to silence. Yet even as we marvel at these frozen clocks near black holes, we recognize that from the falling person's viewpoint, nothing odd happens. This contrast, different perspectives on the same moment, is a reminder that time, unlike a simple river, is part of the tapestry of space-time, relative and personal. If time is part of space-time's fabric, we might picture all events, past and future, laid out in a vast four-dimensional tapestry. In such a block universe, the idea of time flowing is more about our limited perspective. As one physicist quipped, asking, "How fast does time pass?" is as meaningless as asking how fast a second goes by. 1 second per second tells us nothing useful. All moments simply exist, and we move through them, carried by our consciousness. And yet, even knowing this, we cannot shake the feeling that time flows forward. The nature of time reveals a contradiction. Physics says the equations would work fine if time ran backward, but our experience insists on one direction. We remember yesterday, but not tomorrow. We grow older, never younger. The cosmos unfolds like a story, forever turning new pages, never backtracking. Why is that? Why does time have an arrow pointing from past to future? In our everyday life, the forward march of time seems obvious. A sandcastle crumbles in the waves and is gone. We never see the waves spontaneously rebuild it grain by grain. We are born as infants, grow into adulthood, and eventually age, never in reverse. Such observations hint at an underlying principle. Nature moves from order toward disorder. A dropped egg shatters and scatters its yolk, a messy new state that won't leap back into a pristine eggshell. This one-way increase of disorder is enshrined in physics as the second law of thermodynamics. Entropy, a measure of disorder or randomness, tends to increase with time in an isolated system. In simpler terms, as time goes on, things fall apart. It's far easier for glass to break, paint to peel, or our bodies to age than the reverse. This principle gives a kind of arrow to time, the thermodynamic arrow of time. It tells us which way is future. It's the direction in which entropy grows. Every tick of the clock, every natural process, contributes to a little more entropy. Even if we didn't feel time passing, we could, in theory, distinguish past from future by measuring entropy. The past had lower entropy, the future has higher. In fact, it's been suggested that we remember the past and not the future because of entropy. The act of forming a memory increases disorder in the brain, aligning our psychological arrow of time with the thermodynamic arrow. We perceive time flowing forward because the universe is continuously moving toward higher entropy and taking us with it. Yet this answer, satisfying as it sounds, raises a profound paradox. The fundamental laws of physics, Newton's laws of motion, Maxwell's equations for electromagnetism, even quantum mechanics, are mostly symmetric in time. They don't care in which direction time's arrow points. If you watched a billiard ball rebound off a cushion in reverse, the equations would still hold true. On the tiniest scales, an atom or a molecule follows laws that look the same whether time runs forward or backward. As the physicist John Wheeler joked, if you ask an atom about the arrow of time, it will laugh in your face. So how does an irreversible arrow emerge from reversible laws? This is often called the paradox of the arrow of time. We find ourselves in a universe where eggs do break and never unbreak, even though nothing in the microscopic laws says that's mandatory. Scientists have puzzled over this since the 19th century. Ludwig Boltzmann, one of the founders of thermodynamics, explained entropy's rise as a matter of probability. There are more ways for things to be disordered than ordered, so over time we naturally end up in messier states. But one must ask, if disorder increases toward the future, it implies the past was more ordered. Why was the universe so orderly to begin with? This brings us to one of the greatest cosmic mysteries. The early universe, say just after the Big Bang, must have had incredibly low entropy, high order, compared to now. Otherwise, there would be no arrow of time at all, no progression from an ordered state to a disordered one. Left to itself, nature today turns neat arrangements into jumbled ones. If that's always been true, then billions of years ago the cosmos must have been in a very neat, low-entropy condition to start the arrow of time on its way. But why was it in such a special state? This question remains unanswered. Sir Arthur Eddington, who coined the term arrow of time, pointed out that if the universe had existed forever in equilibrium, we'd expect it to be in utter chaos by now. All energy evenly spread out, no stars or life. The fact that we see structure and order means the universe has not been winding down forever. Something set it up young and low entropy once. In Stephen Hawking's words, the arrow of time requires a beginning, a moment of low entropy. Otherwise, eventually everything would have randomized and time's arrow would vanish. Indeed, if the universe were infinitely old and unchanging, The night sky would glow as bright as the sun from the light of endless stars, and all processes would have long run to a standstill. The fact that we see darkness at night and ongoing change suggests time, as we know it, had a beginning. Hawking and others have argued that it makes sense to think time itself began with the Big Bang. In that view, asking what happened before the Big Bang is like asking what's north of the North Pole. It's a question that loses meaning because there is no before when time doesn't exist. According to general relativity, as we trace the expansion of the universe back, we reach a point where densities become infinite, a singularity at time zero. At that singular origin, known laws of physics break down. Any events before that would have no observable effects on what came after, since everything resets at the singularity. So we might as well cut them out of the theory and say that time began at the Big Bang. Hawking famously likened this to the idea that one could travel south until the South Pole, but not further. Beyond that point, south ceases to exist. In his no-boundary proposal, he suggested the universe's beginning might be rounded off like Earth's pole, space and time smoothly forming a cap, with no hard boundary before which one could speak of earlier times. Under that idea, asking about before time began is as meaningless as asking what's outside the universe. Time, in this picture, is finite but unbounded. It didn't come from anything. It simply started. Not everyone is fully satisfied with this conclusion. Some cosmologists entertain daring models in which time may be far grander than our Big Bang. One idea is that our universe's Big Bang might not have been the absolute beginning of time, but rather one chapter in a much larger saga. Could it be that time extends on both sides of the Big Bang, or that Big Bangs happen repeatedly? A group of researchers led by physicist Julian Barber has proposed a scenario in which our Big Bang was a kind of Janus point, a special moment of minimum entropy from which two mirrored universes emerged. In this vision, time branches out in opposite directions. On our side, time flows forward as our universe expands and entropy increases. On the other side, time flows backward as our universe contracts and entropy decreases side. Another universe grows in what we would call the past direction, with its entropy increasing opposite to ours. To an inhabitant of that other universe, time would run the opposite way, but they would experience it as forward, just like we do. Both universes share one low entropy origin, one past, two futures. This strange but simple idea arises from simulations showing that gravity itself can spontaneously generate order. When a swarm of particles interacts gravitationally, they naturally tend to clump into a more ordered state at some moment, then expand outward thereafter. Barber and colleagues argue that this clumping moment could be the Big Bang, a highly ordered state from which the universe expands in both temporal directions, creating a symmetric arrow of time in each direction. Others have imagined the cosmos as an eternal ocean of time, in which occasional islands of low entropy form. Physicists like Sean Carroll and Jennifer Chen, for instance, suggested that perhaps our universe was born as a baby universe branching off from a larger multiverse. In their 2004 proposal, they envision a timeless multiverse in a kind of equilibrium. Once in a rare while, a random fluctuation in this meta-universe could create a pocket of unusually low entropy, essentially a new Big Bang budded off with fresh order. That baby universe, ours, would then evolve forward in time with increasing entropy, developing galaxies, stars, and life, while elsewhere in the multiverse, other universes could sprout with their own arrows of time. In such models, time doesn't begin at one singular event. It has no beginning or end on the grand scale. The idea of an eternal cosmos with local arrows of time is speculative, and many scientists remain cautious. As one cosmologist noted, the notion of a universe without a beginning runs against the prevailing mindset. Still, these proposals remind us that when it comes to the origin of time's arrow, we are still in the realm of educated guesswork. The mystery of entropy in the early universe, why it was so low, is deeply tied to why time flows forward at all. Until we solve that, the arrow of time remains an unsolved puzzle at the heart of cosmology. For now, what we do know is that entropy continues to increase and will shape the fate of our universe. As stars burn their fuel and galaxies drift further apart, the cosmos heads toward a state of ever greater disorder. Trillions of years from now, if nothing intervenes, astrophysicists foresee a desolate scenario. Nearly all usable energy exhausted, stars long extinguished, matter thinned out to a cold haze. This is the ominously named heat death of the universe, a state of maximum entropy where no work can be extracted and nothing ever changes again. In a sense, time's arrow would lose its meaning there, when everything is the same dull temperature and randomness reigns. There are no more events to mark time, no gradients to drive a flow. It's a haunting thought that the arrow which now so decisively points forward may eventually lead to a quiet stillness. But that grim ending, if it comes, lies unimaginably far in the future. For countless eons yet, stars will shine, and life and motion will continue, driven by the drop of sand in the universal hourglass that is entropy's increase. The mystery of entropy isn't only about doom and gloom, it's also about how structure and complexity can exist now. Only a universe that began in a highly ordered state could give rise to galaxies, planets, and living beings before entropy eventually has its say. Thus, our very existence is entwined with the arrow of time. We are creatures of increasing entropy, momentarily thriving in pockets of order, riding a wave that started long ago under mysterious circumstances. Human cultures have long sensed that time might not be a straight line. Many ancient traditions imagined time as cyclical. They observed the cyclical pattern of seasons, the birth and death of generations, the return of comets, and the rhythm of day and night, and saw loops and cycles as fundamental. In Hindu cosmology, for example, the universe goes through infinite cycles of creation, destruction, and rebirth over billions of years. The Maya conceived of time as repeating great cycles. The Greeks spoke of a great year, after which history might reset. And the Stoic philosophers imagined the cosmos periodically consumed by fire and reborn anew. Even without precise science, early peoples intuited something profound. Much of life does move in loops. The moon's phases, the tides, the wheel of life and death. It was comforting to think that eternal return might be nature's plan, that nothing is ever lost, only recycled into the next turn of the wheel. The 19th century philosopher Friedrich Nietzsche took this idea to a cosmic extreme. He pondered, what if time is truly infinite and space is finite? In that case, he argued, every configuration of matter and life might recur endlessly. Nietzsche's concept of eternal recurrence imagined that each of us will live our life over and over again, infinitely, with every joy and every sorrow repeated in exactly the same way. He presented this not necessarily as a literal truth, we don't know if the universe allows it, but as a thought experiment. Could you embrace your life if you knew it would repeat forever? It was a profound, if unsettling, challenge to find meaning in each moment. Modern physics, as far as we can tell, leans toward a one-way journey rather than endless repetition. The observed arrows of time, increasing entropy, the expansion of space, and even certain subatomic decays, all point in one direction, making an exact recurrence of events extraordinarily unlikely. Our universe seems to be expanding relentlessly, not cycling back on itself. Current evidence shows accelerating expansion, which suggests no big crunch to reset things. While some theoretical models like the cyclic universe of Paul Steinhardt and Neil Turok propose that perhaps the universe undergoes periodic big bangs and big crunches, these ideas are speculative and not yet supported by observations. In the Steinhardt-Turok model, our three-dimensional world might collide with another hidden brain universe in a higher dimensional space, triggering repeated big bangs in a kind of cosmic heartbeat. Roger Penrose's conformal cyclic cosmology is another bold idea. He suggests that the remote future of our universe, trillions upon trillions of years ahead, when it's nearly empty, could smoothly transform into the conditions of a new Big Bang, starting a new eon of time. In Penrose's vision, the end of one universe becomes the seed of the next, like a Mobius strip where the timeline loops around on itself. These concepts are fascinating. They weave loops and cycles back into the fabric of cosmic time. If any prove true, time would be both linear and cyclic. Linear within each universe's life, cyclic across universes. At present, such cyclical cosmologies remain unproven, and many scientists favor a simpler picture in which time started at our Big Bang and will not repeat. Still, the allure of cycles persists. We see echoes of eternal return in the orbits of planets and the spin of galaxies. Every day the sun rises, night follows, day follows night, reassuring in its repetition. The earth turns, and we count its spins. One more sunrise, one more year. We know intellectually that each rotation is unique. The configuration of the cosmos is never exactly the same twice. Yet there is poetry in the similarity of these cycles. Perhaps the true cycles that comfort us are the ones of renewal, the spring that follows winter, the way a forest devastated by fire eventually greens with new life. Time, even if fundamentally linear, contains nested cycles that give it texture and pattern. Loops, cycles, and returns remind us that even as entropy increases, there can be repetitions and rhythms within the grand march. The ancient notion that history rhymes, if not repeats, carries a psychological truth. Patterns re-emerge, lessons return in different guises, and something in us finds solace in that continuity. Ultimately, physics suggests we won't literally relive our lives in an identical loop. Nietzsche's demon whispering eternal recurrence seems at odds with the world's fundamental rules. But in the face of time's one-way arrow, we cherish the cyclical happenings we do have, the chance each morning to begin anew. In a universe ruled by time's irreversibility, we create our own little cycles of meaning, our rituals and remembrances, to feel a sense of return and eternal presence. No exploration of time's mysteries would be complete without touching on one of the most captivating questions. Is time travel possible? And if so, what paradoxes lurk in that possibility? In our quiet, reflective journey, even time travel can be considered with gentle wonder rather than Hollywood drama. We are all already time travelers of a sort, always moving into the future at the steady rate of 1 second per second. By adjusting our speed or gravity exposure, We can even move into the future faster than those we leave behind, as Einstein showed. Astronauts aboard the International Space Station, for example, age just a tiny bit less than we on Earth due to their high orbital speed and slightly weaker gravity. This kind of forward time travel, leaping ahead relative to someone else, is not only possible, it's routinely observed and accounted for. GPS, satellites have to correct for time dilation so that their clocks stay synced with ground time. So traveling into the future is real, though practical limits, needing near light speed, for instance, keep it in the realm of minute or hour differences for now. The real conundrum, however, is traveling to the past. This is where the quiet dilemmas emerge. Imagine you had a machine that could take you back years or centuries. The paradoxes appear almost immediately. The most famous is the grandfather paradox. Suppose you went back and prevented your own grandfather, or any ancestor, from meeting your grandmother. Then you would never be born. But if you were never born, who travelled back to prevent anything? The logical loop is perplexing. Any change you attempt in the past that disrupts the chain of events leading to the present could undermine the very reason you travelled back in the first place. It's a quiet but profound dilemma. The universe would be caught in a contradiction. Another paradox is the bootstrap paradox, or ontological paradox, where an object or piece of information is sent back in time and becomes trapped in an endless loop with no clear origin. For example, a traveller from the future hands young Beethoven a copy of his own sheet music, enabling him to compose his symphonies. Who originally wrote the music? It seems to emerge from nowhere, existing in time only as a loop. These scenarios tickle the mind and make for great storytelling, but they hint at a universe that might not permit such inconsistencies. What do physicists say? Einstein's general relativity does have odd solutions, like wormholes, shortcut tunnels through spacetime, or a spinning infinitely long cylinder, or cosmic strings, that mathematically allow paths which loop back in time. These are known as closed time-like curves. However, just because the equations allow them doesn't mean they can actually exist in our universe. Stephen Hawking suspected they cannot. He proposed a chronology protection conjecture, essentially a law of nature that forbids time machines, thereby making the universe safe for historians. In other words, physics might contain subtle mechanisms, perhaps quantum effects, that prevent paradox-inducing time travel. For example, approaching a scenario that would create a closed time-like loop might always require conditions, like negative energy densities or perfectly rigid infinite cylinders that are physically unattainable. It's as if the universe has built-in safeguards against causality violation. Intriguingly, recent theoretical work has suggested that even if time travel to the past were possible, the universe might self-consistently avert any paradox. One study in 2020 by a young physicist, Jermaine Tobar, found mathematical solutions implying that if you tried to change the past, events would adjust around you to prevent any inconsistency. For instance, imagine you went back in time to stop a pandemic from starting. Perhaps you managed to prevent patient 0 from being infected. According to these calculations, something would happen to ensure the pandemic still unfolds one way or another. For example, you might inadvertently become the new patient 0 and set off the very outbreak you sought to prevent. No matter what you did, the overall outcome would recalibrate to align with the history that leads you to go back in time in the first place. In such a scenario, the timeline is elastic but unbreakable. You can bend events, but you cannot create a paradox. The future you came from might end up unchanged by your interference, or your actions might even be the cause of the history you already knew, a predestination paradox. This is reminiscent of many science fiction plots where, despite the hero's efforts to alter fate, they end up fulfilling it. It's a logically consistent possibility. Time travel, without true free will, to alter events. Of course, these ideas are speculative and assume time loops can exist at all. As the researchers themselves acknowledged, proving that time travel is mathematically consistent is not the same as showing it's physically achievable. To actually build a time machine, one might need exotic conditions, like wormholes held open by negative energy, that we're nowhere close to realizing, if they're possible at all. And even if one could theoretically travel back, the quiet dilemmas of potentially meddling with causality raise profound questions about determinism and free will. Perhaps in the end, nature spares us these dilemmas by keeping time travel forever out of reach. Or, if time travel to the past is possible, perhaps the only logical paths through time are those that do not allow you to change history in any inconsistent way. For now, we have no evidence of time travelers in our midst, no unexplained whispers from the future guiding our present. All we have are tantalizing hints from physics that time is more flexible than our intuition suggests, but likely not so flexible as to tie itself in logical knots. In a sense, the mystery of time travel is a mirror to the mystery of time itself. Both remind us how little we truly understand causation and temporal existence, and both, for now, remain in the realm of imagination, inviting us to wonder, but keeping their secrets. Having wandered through the far reaches of cosmic time, from the universe's birth to its possible end, from the flow of entropy to the notion of reversing the arrow, from cycles of eternity to flights of time travel fancy, we arrive at a gentle realization. Time, with all its puzzles, surrounds us in every fleeting second. We began by asking, what is time? And perhaps expected a crisp scientific answer. Instead, we found that science, philosophy, and imagination together paint time as a rich mystery, a dimension we move through but barely comprehend. We've learned that time can bend and slow, that it may have a beginning and perhaps an end, that it points inexorably forward, yet leaves us free to dream of looping back. We've seen that even the greatest minds, Newton, Einstein, Hawking, ultimately had to admit uncertainty about time's full nature. In the face of such uncertainty, one might feel unsettled, but there is also a profound peace in it. Time's enigma invites us not only to scientific inquiry, but to philosophical reflection on our own lives. All we ever really have is the present moment, this moving now, which immediately slips into the past as a new moment arrives. We cannot hold it, just as we cannot grasp water in a clenched fist. Yet the present is where we live, where we feel and act. Perhaps, as some thinkers have suggested, the distinction between past, present, and future is more fluid than it seems. Albert Einstein mused that the separation between past, present, and future is only a stubbornly persistent illusion. All moments might exist in the tapestry of spacetime, and our consciousness lights them up one by one, like fireflies along a path. If that is so, then maybe every moment is eternal in its own way. The moments that have passed aren't gone. They're just not illuminated anymore for us. And the moments yet to come already exist, waiting for us to arrive. Whether or not that is literally true, it's a comforting thought. Nothing cherished is truly lost in time. It's preserved in the cosmic archive of was, and what will be is already written in the stars, though unseen by us. In the end, after all the scientific theories and fantastical possibilities, we return to ourselves, living in time. We find that the mystery of moments is something to savor rather than solve. Each moment we experience is unique in the history of the universe, a fleeting configuration that will never come again. Knowing what we know now, that time might be an illusion, that the arrow of time is precious, that the present is all we directly possess, we can choose to embrace the now with a quiet awe. The writer Henry David Thoreau once advised, "Live in the present, launch yourself on every wave, find your eternity in each moment." Indeed, there is a kind of eternity in the present moment when we fully attend to it. The past is memory, the future conjecture. The now is where life happens. We can let go of trying to control time's passage and instead rest in the mystery of the moment. Here, at the close of this part of our cosmic journey, we do not find a neat conclusion about time, for time's riddles remain unsolved. Instead, we find a sense of wonder and acceptance. The flow of time may be an enigma, but it is also the gentle rhythm of our lives. We feel it in our heartbeat, in the waxing and waning of the moon, in the aging of a loved one's face. Each moment whispers of the great cosmic story, yet also stands complete in itself. As we pause now, between past and future, we allow ourselves to simply be, suspended in the quiet of the present. In that stillness, the mystery of time hums around us like a cosmic lullaby, not demanding answers, only inviting contemplation. We have journeyed through deep space and deep time, and though we have not solved the cosmic enigma, we have felt its presence. In the next steps of our exploration, other mysteries beckon us onward. But for now, we linger a moment longer in the hush of the now, content to marvel at time, the ever-unfolding, ever-unfathomable medium of our existence. In the silent aftermath of a star's death, its scattered ashes enrich the surrounding cosmic clouds with heavy elements. Within one such vast, dark nebula, a new story quietly begins. The nebula drifts cold and quiet in the starlight, harbouring tiny grains of dust and gas. All is still for ages, until a gentle disturbance, perhaps the distant shockwave of a supernova or a passing star, stirs the cloud. Slowly, under gravity's ancient spell, parts of the cloud begin to gather and collapse inward. Deep inside the contracting cloud, clumps of material grow denser and warmer. What was once a diffuse haze now forms a hidden core, squeezing tighter as it pulls in more mass. Temperatures climb in this buried protostar, a star to be still cloaked by dust. In these lightless depths, atoms of hydrogen are pressed closer and closer together. The cloud begins to spin as it falls inward, and a swirling disk of gas and dust flattens around the growing core. Through the eons-long collapse, the protostar feeds on the infalling material, growing in mass and heating up further at its centre. At first, not a hint of this birth escapes the dark nebula. No visible glow breaks the darkness. But as the protostar gains strength, it starts to emit a faint warmth and light of its own. Jets of gas erupt from its poles, carving out cavities in the surrounding cloud. The newborn star is impatient to reveal itself. Bit by bit, its radiance pushes away the shrouding dust. After millions of years of quiet gestation, the core becomes hot and pressurized enough that a profound transformation ignites within. Hydrogen nuclei begin to fuse into helium. In that moment, a star is born in earnest, shining with its own light. The new star's first light is gentle, filtering through the remaining veils of its natal cloud. This infant sun glows steadily now, held together by gravity and powered by the fire in its core. It will continue to contract slightly until an equilibrium is reached, gravity pulling in, energy pushing out. Once stable, the star joins the cosmic panorama as another point of light among billions. Scattered across our galaxy, countless stars are being born in similar cradles of gas and dust at any given time. Each emergence is a slow, silent miracle, unfolding on timescales far beyond human life. Our own sun was once one of these quiet newborns. Over 4.5 billion years ago, in a nebula rich with the debris of earlier stars, the sun's journey began as a collapsing globule of gas and dust. We can imagine that ancient scene, a gentle amber glow burgeoning in the darkness, destined to become the brilliant star that lights our skies today. Every star in the night sky has a similar origin story, a tale of patience and gravity, of darkness giving way to starlight. Now that a star has come to life from the cold void, a natural question arises. What causes that steady glow? What makes a star shine so persistently, sometimes for billions of years? To uncover the secret of a star's light, we must journey into its core, an extreme realm hidden from any direct sight. The newborn star's center is tremendously hot and dense, millions of degrees and crushing pressures beyond imagination. In this cauldron, the fundamental forces of nature perform an extraordinary alchemy. The most common element in the universe, hydrogen, is transformed into helium in a process that releases an immense amount of energy. This process is nuclear fusion, and it is the engine that makes each star shine. Inside the star's fiery heart, hydrogen atoms collide at such high speeds that they fuse together. With each fusion, a tiny bit of matter converts into pure energy. Over countless reactions, these bits of energy add up to a brilliant outpouring of light and heat. The energy fights its way outward from the core, radiating through layers of plasma. After a long journey, sometimes thousands of years bouncing around inside, the energy reaches the surface and escapes into space as the glow of starlight. This is why, from immense distances, we see a star twinkle. We are witnessing energy that was forged in the stellar core, now free to traverse the cosmos. For many millennia, the fact that stars shine seemed magical and mysterious. Ancient sky watchers imagined campfires of the gods or celestial lanterns hung in the firmament. Only in the past century did science finally unravel this deep mystery. When we learned about nuclear fusion, it explained not only why stars shine, but how they can keep shining for such incredibly long times. A star like our sun can burn steadily for billions of years, its core acting as a self-sustaining furnace. Smaller, dimmer stars sip their fuel slowly and may shine for trillions of years, while the most massive stars blaze through their supply in mere millions. Yet the basic mechanism is the same in all: the conversion of mass into energy in the stellar core. Equally wondrous is how a star remains stable as it shines. In the core, the furious energy generation creates pressure that pushes outward, and this outward pressure perfectly balances the inward pull of the star's gravity. The star finds an equilibrium, neither exploding outward nor collapsing inward, but quietly humming along in a delicate cosmic balance. It is a harmony of forces that keeps the star steady and luminous over eons. As long as there is fuel in the core, gravity and pressure maintain this serene standoff, and the star's light does not falter. The sunlight that bathes our world each day is a direct gift of this process deep within the sun's core. Every ray of sunshine that warms your skin began as an energetic photon generated by fusion reactions, an unimaginable distance and time away at the sun's center. The life we know on Earth is nurtured by that energy. In this way, a star's shine is not just a distant sparkle. It is the source of light and warmth that can make planets habitable. We owe our existence to a star's steady glow. Now imagine the scene around a young star that has just turned on its light. The darkness that once prevailed in the surrounding space is chased away by a growing sphere of illumination. Dust and gas that were invisible in the void now glint in the star's new light. This newborn sun is not alone. It is surrounded by the remnants of the very cloud that formed it. That leftover material orbits as a vast disk. Bathed in the star's radiance, this spinning disk of gas and dust is destined for its own dramatic transformation, the birth of planets. Around the young star, the scene is one of cosmic dusk and promise. A broad disk of gas and dust stretches out around the star like a great, flat ring. This is the planetary nursery, the leftover material from the star's formation, now destined to create an entire system of worlds. Up close, it would look like a vast expanse of drifting particles, from microscopic dust grains to larger clumps of rock and ice, all orbiting in a thin plane. The star's new light faintly illuminates this disk, revealing swirling patterns in the haze. Within this swirling disk, countless collisions and coalescences are quietly underway. At first, the dust grains stick together gently, held by fragile electrical charges when they bump. Over time, these grains form tiny clusters, which merge into pebbles, then rocks. Millions of such grains are assembling like cosmic clay, merging whenever they meet. As the pieces grow larger, gravity begins to assist, tugging in more material. The process quickens. Rocks accumulate into boulders. Boulders gather into mountain-sized chunks. These embryonic building blocks are known as planetesimals, and they roam the disk like a swarm of newborn world seeds. The environment in the disk is chaotic. As planetesimals sweep through, they sometimes collide violently, shattering each other, but other times they merge, growing bigger with each impactful embrace. The young star's radiation is also at work, gradually blowing away the lightest gases from the inner regions and clearing the way for solid matter to clump. Over a few million years, distinct regions in the disk begin to emerge. In the warmer inner zones, metals and rocks dominate, laying the groundwork for small, rocky planets. Further out, where it's colder, ices and gases can coalesce, giving rise to larger, gaseous planets and icy moons. In time, several large bodies assert themselves, carving paths in the disk. We have caught glimpses of these distant planetary nurseries with our most powerful telescopes. They often reveal breathtaking patterns, concentric rings and gaps in the dust, like ripples in a pond. These gaps are the footprints of newborn planets, ploughing through the disk and accumulating material as they orbit their star. Astronomers were astonished when the first clear image of such a disk showed dark rings, evidence that even infant stars can host forming planets earlier than we expected. Each disk we observe has its own character, some with neat circular bands, others with spiral arms or dense clumps. These variations are the subtle signatures of planets coming to be, each system writing its own creation story. Despite the progress we have made in observing planet formation, many secrets remain. It is still a mystery how some planets grow to enormous sizes so quickly before the disk's gas is dispersed by stellar winds. Our own cosmic neighborhood offers puzzles too. Why did our solar system end up with small rocky planets near the Sun and gas giants farther out, when many other systems show giant planets hugging close to their stars? How did Earth acquire its water and rich organic materials that allowed life to flourish? The planetary nursery holds the answers to these questions, but it guards them carefully, revealing clues only bit by bit through our investigations. In our solar system's nursery, billions of years ago, the Earth was assembled from countless collisions and likely received water and other crucial ingredients from the outer reaches. Comets and water-rich asteroids may have bombarded the young Earth, delivering the gift of oceans and complex molecules. By the time the Sun's stellar winds blew away the remaining nebula gas, a family of planets had taken shape around our star, each carrying its own portion of the initial disk's materials. The stage was set. A warm, rocky world with oceans and all the necessary elements was orbiting in the gentle glow of the Sun. The basic planetary architecture was in place, and the raw ingredients for something remarkable were present. In the newborn Earth's oceans and atmosphere lay the chemical seeds of life, delivered by the cosmic processes that built our planet. Yet those seeds, water, carbon, and all the vital elements, did not originate on the Earth itself. They were inherited from the larger universe, from events that took place long before our planet formed. In truth, every atom in our bodies and every drop of water in the sea has a history that reaches beyond Earth. To uncover the origins of life's ingredients, we must journey to the furnaces where the elements were forged and follow their path through space and time. Long before Earth took shape, the universe was preparing the ingredients for life in the hearts of stars. In the beginning, after the Big Bang, there were no planets, no water, and none of the carbon or oxygen that life relies on. The early cosmos contained mostly hydrogen and helium gas, the simplest elements. The heavier elements, carbon, nitrogen, oxygen, phosphorus, and so on, had to be manufactured in the furnaces of stars. As the first generations of stars lived and died, they forged new elements in their cores through fusion, and in their final moments, some of them exploded as supernovae, casting those elements out into space. It was through this cosmic cycle of star birth and death that the raw materials for life were gradually built up and spread across the galaxy. Every atom of carbon in our bodies was synthesized in a star. Every oxygen atom we breathe was once locked inside a star's core, or formed in the blast of a supernova. We truly are, in the literal sense, made of star stuff. Over billions of years, countless stars contributed to enriching the galaxy with elements beyond hydrogen, clouds of gas that had been seeded with those new elements eventually condensed to form new stars and their surrounding planets. Our Sun is one of those later generation stars, born into a galaxy already laden with the ashes of ancient stars. That is why the material that coalesced into Earth contained all the necessary elements for building water, rocks, and organic molecules. Along with elements, the universe also provided simple compounds and a head start on chemical complexity. In the cold depths of interstellar space, within giant molecular clouds, atoms combine on the surfaces of dust grains to form molecules. For example, hydrogen and oxygen come together as water, even in space, freezing onto dust particles. Organic molecules, those based on carbon, also take shape in these cosmic laboratories. Scientists have detected over 100 different molecules in interstellar clouds, including alcohols, simple sugars, and nitriles. These clouds, when they collapse to form new stars and planets, carry this chemical inventory into the new systems. As planets were forming around our young sun, they inherited this wealth of cosmic materials. We have evidence of this inheritance preserved in the ancient remnants of the solar system. Meteorites that have fallen to Earth from space are like time capsules from the early solar nebula. Remarkably, some meteorites contain a rich assortment of organic compounds. In one famous example, a meteorite that landed in Australia was found to contain dozens of amino acids, the building blocks of proteins, many of which are identical to those used by life on Earth. Even more astonishingly, recent studies of meteorites and comet samples have revealed the presence of the nucleobases, the very letters of DNA and RNA. All 5 primary bases that encode genetic information have been identified in meteorite samples, implying that the basic alphabet of life's genetics was being sprinkled onto the early Earth from space. Additionally, a recent spacecraft mission returned samples from a near-Earth asteroid, Bennu, revealing abundant organic matter, including amino acids and those same genetic bases, sealed within a fragment of primordial space rock. These findings reinforce the idea that the early Earth was showered with life's pre-made ingredients, delivered ready-made from the cosmos. Comets and asteroids bombarding the young Earth likely delivered significant amounts of water and organics to our planet's surface. The water in Earth's oceans may be as much an extraterrestrial import as a native supply. Modern measurements have even found that the chemical fingerprint of water in some distant protostellar disks matches that of water in our solar system, suggesting a continuity of water from the interstellar cloud to the planets. In essence, the Earth was seeded with water that was older than the sun, ice that condensed in the frigid darkness of space before our sun began to shine. Along with water came carbon-rich molecules, setting the stage with a planetary broth rich in possibilities. The result of all these contributions was a young Earth stocked with the essential ingredients: liquid water pooling on the surface, an atmosphere with various gases, and a menagerie of organic molecules drifting in the seas and skies. These included amino acids, simple sugars, and fatty compounds that could form primitive membranes. Everything necessary, it would seem, for life's chemistry to commence. Nature had provided the raw materials across eons and light years, gathering them on this infant world. But having the ingredients in place is one thing. Assembling them into something alive is another. How did Earth's chemistry take that next step into biology? This question of how life first arose from non-life, the question of abiogenesis, remains one of the deepest mysteries in science. Even with all the right pieces on the board, the emergence of life is not guaranteed. Scientists continue to puzzle over the exact sequence of events and conditions that sparked the first living organisms. Perhaps it happened in a warm little pond, as Charles Darwin once mused, with sunlight and lightning fueling reactions in a concentrated soup of molecules. Or perhaps life's inception took place in total darkness, around a deep-sea hydrothermal vent on the ocean floor, where mineral-rich hot fluids mix with cold seawater, creating a chemical playground. There is even the possibility that life's first building blocks formed elsewhere, on Mars or another world, and travelled to Earth aboard a meteorite, meaning life's ingredients not only came from space, but life itself might have had an extraterrestrial trial run. We do not yet know. To delve deeper into this enigma, we must look at what science has uncovered and still struggles to understand about abiogenesis. Abiogenesis refers to the process by which living organisms arise from non-living matter. It is, in essence, the answer to how chemistry became biology on the early Earth. Despite decades of research, abiogenesis remains elusive and only partially understood. Still, scientists have pieced together plausible narratives for how life might have taken its first tentative steps. These scenarios are like pieces of a puzzle that we are slowly fitting together to see the bigger picture of life's dawn. One classical idea is the primordial soup hypothesis. Imagine the young Earth over 4 billion years ago. Volcanic landscapes, steamy pools of water, and an atmosphere filled with gases like methane, ammonia, and hydrogen. Frequent lightning storms and intense ultraviolet sunlight bombarded this environment with energy. In theory, these conditions could drive simple molecules to assemble into more complex ones. In a famous experiment in 1953, scientists replicated these early Earth conditions in glass flasks. After running electrical sparks through a mixture of primitive atmospheric gases and warm water, they found that amino acids had formed spontaneously in the flask. In just a few days, the once clear mixture had turned cloudy and pinkish, with newly made organic molecules. This landmark result showed that the building blocks of proteins could indeed arise from basic chemistry, supporting the vision of a primordial soup where life's ingredients brewed over time. It was a striking demonstration that the basic chemistry of life could emerge naturally from non-living ingredients. While the primordial soup provides a broad canvas, other researchers have sought more structured settings, where life's precursors could concentrate and react. One such setting lies in the deep ocean, at hydrothermal vents. These vents, which still exist today along mid-ocean ridges, spew hot, mineral-rich water into the surrounding sea. Around them, unique ecosystems of microbes and strange creatures thrive on chemical energy rather than sunlight. The idea is that early in Earth's history, similar vents could have provided a rich chemical playground. The rocks around vents contain pores and chambers that might have served as natural test tubes, concentrating molecules and catalyzing reactions. In these warm, sheltered nooks, complex chemistry might have progressed in stages towards life, shielded from the chaos of the surface. All the while, the vent environment would continuously supply energy to fuel these reactions. Another hypothesis focuses on surfaces like clay or other minerals as platforms for assembly. Clay particles in ancient mudflats or tidal pools might have attracted and held on to organic molecules, bringing them into close proximity. Some minerals can also promote chemical reactions by providing surfaces where molecules line up in orderly ways. Through cycles of wetting and drying, say, with tides or rain and evaporation, simple organic compounds could have polymerized into longer chains. For instance, RNA, a molecule believed to be critical in early life, can form from simpler components under the right conditions, and mineral surfaces might assist this formation. Such processes hint at how non-living chemistry could gradually acquire the properties of life, such as the ability to store information and replicate. It suggests that even in the absence of life itself, a prebiotic chemistry could have progressively organized itself, step by step, into something approaching biology. Indeed, laboratory studies have shown that cycles of drying and wetting can drive the formation of long molecular chains, like RNA, hinting that nature could take incremental steps toward life. A key focus in origin of life research is identifying a molecule or system that could have been the first to self-replicate. Many scientists suspect that RNA, which can both store genetic information and catalyze chemical reactions, was a prime candidate in early life. This is known as the RNA world hypothesis. In an RNA world, small RNA molecules might have formed and eventually gained the ability to make copies of themselves. Once a molecule could replicate, even with occasional errors, Darwinian evolution could kick in, favoring those molecules better at surviving and reproducing. Over time, a network of chemical reactions might have become more organized, eventually leading to the first primitive cells. Still, moving from complex molecules to the simplest cells is a huge leap. A cell needs a boundary, like a membrane, a way to harness energy, and a method to reproduce. Experiments have shown that fatty acids can spontaneously form tiny bubbles, or vesicles, in water, essentially forming rudimentary membranes. These bubbles can encapsulate other molecules, creating a microenvironment. One can imagine an early scenario where such vesicles trapped self-copying RNA or other chemicals, forming a primitive protocell. If that protocell could grow and split, dividing its contents, it would resemble reproduction. Such simple vesicles, combined with replicating molecules, might have been stepping stones to the first true living cells. Despite these intriguing ideas, no one yet knows exactly what sequence of events led to life's origin on Earth. Perhaps multiple pathways were explored by chemistry, with only one succeeding and leaving a legacy that became all of life as we know it. What we do know is that life arose relatively quickly in geological terms. Earth formed around 4.5 billion years ago, and there are hints of microbial life appearing as far back as 3.7 to 4.0 billion years ago, not long after the planet had cooled enough to support oceans. This suggests that under the right conditions, the emergence of life might not be exceedingly rare, at least on a planet like ours. But whether life's spark was easy or extremely improbable remains an open question. Scientists continue to experiment, mixing various recipes of early Earth ingredients in the lab and even in simulations, trying to coax lifelike behaviors from non-living chemistry. They have made significant progress, creating amino acids, sugars, nucleotides, and even protocells under simulated primordial conditions. But they have not yet achieved a self-sustaining, reproducing system that everyone agrees is alive. Each breakthrough, however, gives insight. For example, we've learned that certain combinations of amino acids can form protein-like droplets, or that cycles of hot and cold can drive RNA to copy itself in a rudimentary way. Piece by piece, these findings illuminate possible steps on the path to life. The question of abiogenesis is more than just about Earth. It carries profound implications for life elsewhere. If life emerged relatively readily on Earth, given the ingredients and environment, perhaps life could be common in the universe wherever similar conditions exist. On the other hand, if there were extraordinary 1 in a trillion flukes involved, we might be unique. At this point, we simply have insufficient data to say. All we can do is continue exploring and experimenting. In the rocks of ancient Earth, scientists hunt for fossils and chemical signatures that might hint at how the earliest life lived. In the laboratory, they strive to recreate life's first spark. And as we look out into the cosmos, we keep our eyes open for signs that nature may have performed this grand experiment elsewhere too. In pondering abiogenesis, one cannot help but wonder whether life had multiple false starts. Did life only begin once in the universe, or even on Earth, in the form of a single lineage that gave rise to everything alive today? Or could life have originated many times, in many places, with only some instances surviving or evolving further? These questions lead us to consider the uniqueness of our biochemistry and whether alternative forms of life could have arisen and perhaps still lurk undetected. The notion that life might have begun once, or more than once, raises fascinating possibilities about the prevalence of life in the universe and the singularity or commonality of our own origin. Every living thing we know on Earth shares a common biochemical foundation. From the mightiest tree to the tiniest bacterium, all used DNA or RNA as genetic material, the same 20 amino acids to build proteins, and the same energy currency in cells, ATP. This unity suggests that all known life descended from a single origin, one ancient ancestor, often called the last universal common ancestor, LUCA. It appears that life began once, at least in the lineage that led to us, and every organism we've ever observed is part of that one family tree. But is it possible that life could have begun more than once on our planet, only for one lineage to outcompete or overshadow the others? Scientists have pondered the idea of multiple genesis events on Earth. If early Earth had several environments where life could spark, perhaps life got started independently in more than one of them. Imagine, for instance, life emerging in a shallow lagoon while another unrelated form of life begins around a hydrothermal vent. Could these separate life forms have coexisted? If they did, perhaps the more efficient or lucky one spread and became dominant, while other nascent life forms perished. Over billions of years, all traces of any alternate origin might have been lost, absorbed into the victorious lineage, or rendered unrecognizable. This is one hypothesis, that life may have tried to get started several times, but only one attempt succeeded long-term. How would we know if life had begun more than once on Earth? One way to find evidence would be to discover organisms that fundamentally differ from all known life. Thus far, despite the immense variety of life, everything we've studied fits the same basic template. For example, bacteria found in boiling hot springs, or even in radioactive waste, still rely on DNA, proteins, and the same basic chemistry as all other known life. Microbiologists have scoured extreme environments for any sign of a shadow biosphere, life with a different biochemistry, perhaps using alternative amino acids, or a different genetic code, or even a solvent other than water. So far, no incontrovertible evidence of such alien biology on Earth has been found. Every microbe, no matter how strange its lifestyle, whether living in boiling acid or under crushing pressure, still shares the familiar chemistry of our known life. If a truly separate form of life exists here, it has eluded detection. However, the absence of evidence is not necessarily evidence of absence. Life as we know it is very good at filling ecological niches, which means any alternative life, if it ever arose, might have been outcompeted early on. Imagine an early Earth scenario where multiple proto-life forms appeared. The one that evolved more efficient replication or metabolism could rapidly spread and monopolize resources, preventing others from taking hold. Alternatively, different forms of early life might have even swapped genetic material, blurring distinct lineages into one. It's also possible that conditions favorable for life's origin might have been rare and fleeting, allowing only one success. Without clear fossil or chemical evidence from that very distant past, these ideas remain speculative. Another angle to this question comes from looking beyond Earth. If we find life on another world in our solar system, say on Mars, or in the subsurface ocean of Europa, and if that life is based on a completely independent origin, it will tell us that life can begin more than once in the cosmos, and perhaps even that multiple starts are the norm. If, for instance, we discover microbes on Mars that have a biochemistry incompatible with Earth life, we would know those organisms do not share our LUCA. That would be a profound revelation. 2 genesis events within one solar system. On the other hand, if any extraterrestrial life we find has a biochemistry similar to our own, it might hint at a common origin rather than an independent genesis. Perhaps life was transferred between planets by meteorites, a concept known as panspermia. If so, then life may have begun only once in our cosmic neighborhood and simply spread to multiple worlds. Researchers also examine Earth's earliest history for hints of multiple origins. Some studies look at the genetic code and molecular machinery of life to see if it could bear scars of a time when different genetic codes competed, or when life's chemistry was not yet unified. There are curious hints, like certain amino acids being left-handed exclusively in life, while non-living chemistry produces both left and right-handed versions. Why life turned left instead of right remains a mystery. One thought is that perhaps one form of life with a particular orientation prevailed over another. Likewise, all life using DNA and RNA could have suppressed a hypothetical form of life that perhaps used a different genetic molecule. For instance, one could imagine a primordial microbe with a different genetic system that was ultimately eliminated or absorbed by the ancestors of modern DNA-based life. It's a provocative notion, but one that remains entirely speculative without any concrete evidence. Ultimately, as far as we can tell today, all life we see around us is related. Life may well have begun only once in our observable lineage, making us singular in origin, at least locally. But the question remains open because it's very hard to prove a negative. We cannot be absolutely certain that no other form of life ever took root here. The best we can do is continue to search. If we ever find a microbe that shares no ancestry with us, or a fossil of something with an utterly foreign biochemistry that would answer the question, until then, the idea of multiple origins on Earth remains an intriguing possibility without confirmation. What about life beyond Earth? The universe is vast, and if the ingredients and conditions for life are widespread, life could have begun countless times on countless worlds. If life began quickly here, some argue it might readily arise elsewhere when conditions are right. In that case, the cosmos could be teeming with biochemistries and ecosystems, each an independent origin. Conversely, if life's start required an improbable chain of events, maybe it only happened rarely, perhaps only here. As we plan missions to Mars, Europa, Enceladus, and beyond, one underlying motivation is to find a second genesis of life. Just one confirmed example of life that did not originate on Earth would tell us that the universe likely brims with life. It would transform our understanding from life being a near miraculous fluke to perhaps an expected outcome of cosmic processes. It would confirm that life is not a solitary miracle, but a fundamental part of the cosmos. Our inquiries into whether life began once or many times lead naturally to another profound mystery: the search for life beyond our own planet. For now, we grapple with our single data point, Earth, which both hints that life can arise, because it did here, and cautions us that we have nothing to compare it to. As we continue to explore this question, we venture further out, looking to other worlds for answers. In the meantime, closer to home, there are other refuges that could harbour life's second genesis. If not on Earth's surface, then perhaps hidden in places we've only begun to explore. This brings us to the silent, dark oceans concealed beneath ice on distant moons and the possibilities they hold. Scattered through our solar system are worlds that hide dark oceans beneath their frozen crusts. These secret seas have never seen sunlight, yet they contain the essential ingredient for life as we know it: liquid water. One of the most intriguing is Jupiter's moon, Europa. Beneath Europa's icy exterior, which is crisscrossed with cracks and ridges, lies a global ocean of salt water. This hidden ocean may be in contact with a rocky seafloor below, potentially allowing mineral-rich water to circulate, a condition much like Earth's own oceans, where life flourishes around hydrothermal vents. Despite the Moon's surface being bombarded by deadly radiation from Jupiter, the water beneath remains shielded and dark, a silent world unto itself. Not far from Europa, another moon whispers possibilities of life. Enceladus, a small moon of Saturn, also harbours a liquid ocean under its ice. In a spectacular cosmic fountain, Enceladus continuously ejects geysers of water vapour and ice particles from cracks near its south pole. These plumes, venting out into space, have allowed scientists to taste the Moon's inner ocean indirectly. As the Cassini spacecraft flew through Enceladus's geyser spray, it detected organic molecules and tiny grains of rocky material, hinting that hydrothermal reactions might be occurring on the seafloor below. Even more recently, researchers discovered that Enceladus's plumes contain phosphorus, a critical element for DNA and cell membranes, at surprisingly high levels. This discovery was thrilling, as it means Enceladus's ocean contains all of the key elements that life as we know it requires. At least from a chemical standpoint, Enceladus now checks all the boxes for potential habitability. Then there is Titan, Saturn's largest moon, shrouded in a thick golden atmosphere. Titan's surface is paradoxical. It has lakes and rivers, but they are filled with liquid methane and ethane instead of water. However, beneath Titan's frigid surface of water ice, scientists strongly suspect another hidden water ocean resides. Titan's internal ocean, kept liquid by the Moon's internal heat and the pull of Saturn's gravity, could be a habitable zone completely isolated from the strange chemistry on the surface. Titan's subsurface water hasn't been directly sampled, but its existence is supported by measurements of Titan's rotation and gravity field. If life exists in Titan's under-ice sea, it might be quite different from life in a sunlit environment, perhaps drawing energy from slow chemical reactions in the dark. Deprived of sunlight, any organisms in that ocean would have to rely solely on chemical energy to survive. We have no evidence yet that anything is alive in Titan's hidden sea, but the possibility keeps scientists curious. Titan remains a compelling target for future exploration, as its combination of rich surface organics and a buried ocean makes it an intriguing dual world of chemical complexity. Even more distant and surprising, tiny Pluto, once considered a barren ice ball, may also possess a hidden ocean beneath its frozen plains. The New Horizons spacecraft's flyby of Pluto in 2015 revealed surface features that suggest a subsurface ocean that has not entirely frozen. Other bodies, like Neptune's moon Triton or several of Uranus's moons, are also candidates. It seems that throughout the outer solar system, where sunlight is scarce, internal heat and tidal forces can maintain liquid water deep below the surface. Each of these concealed oceans is essentially a world within a world, isolated by kilometers of ice and rock from the rest of the cosmos. If life had a second genesis in our solar system, these subsurface oceans are among the most promising places it might be found. They offer stable environments, rich in water, and shielded from harsh cosmic radiation and meteoric bombardment. On Earth, life has proven that it can thrive in complete darkness around hydrothermal vents and within subterranean rocks, drawing energy from chemistry instead of sunlight. Sealed beneath thick ice, such oceans are protected from intense radiation and impacts that bombard a planet's surface. By analogy, microbes could potentially live in the abyss of Europa's or Enceladus's ocean, feeding on minerals and warmth from the Moon's core. Perhaps only thin microbial mats or single-celled organisms could persist there, clinging to whatever warmth and nutrients seep from the moon's interior. They would be utterly cut off from our world, living and dying in silence under the ice, perhaps never evolving beyond simple forms. Yet even the mere presence of microbes there would be revolutionary, evidence that life is not unique to Earth. The silence of these hidden oceans is both literal and metaphorical. No sunlight penetrates their depths, and if any creatures stir there, they likely do so without eyes or voices that we would recognize. For eons, any biosphere beneath an ice shell would remain undetected by the universe at large, a private ecosystem under a cold ceiling. Only through indirect clues, a plume of water here, a slight wobble in a moon's orbit there, have we come to suspect their existence. It fires the imagination to picture an alien ocean floor in perpetual night, dotted with warm springs where simple life clusters for warmth and nutrients. In the coming years, our robotic explorers will probe these silent seas. NASA's Europa Clipper mission is slated to launch and will orbit Jupiter, investigating Europa's ice shell and ocean with sensitive instruments. There are concepts for missions to land on Europa or Enceladus, to drill or melt through the ice, or even to send a submersible robot into the waters below. These endeavors are technologically daunting, but the payoff could be immense. A chance to find living organisms or telltale chemical traces of their presence. Even a whisper of life, a complex organic molecule out of place, a hint of metabolism, would echo loudly in human history. For now, the existence of life in these hidden oceans remains speculative. We must be patient and ingenious in our search. Each of these moons and distant ocean worlds challenges us to look deeper and think differently about habitability. Life, if present, might be sparse and slow-growing, perhaps just microbial mats lining warm cracks in the ocean floor. Or it could surprise us, maybe thriving ecosystems with strange blind fish-like creatures, though few scientists expect such complexity in these environments. The possibilities remain open and quietly beckoning. Until we explore directly, the oceans of Europa, Enceladus, Titan, and others will keep their secrets, silently waiting beneath ancient ice. As we contemplate these concealed seas and what they might harbour, we are reminded that the spark of life can be tenacious, finding a foothold in the most unlikely places. The search for a second Genesis in our backyard has profound implications. If we discover life in one of these oceans, it means life likely abounds in the universe wherever conditions are favourable. If we search diligently yet find nothing, that too tells us something, that perhaps we are more alone than we hoped, or that life needs rarer conditions. Either outcome would deepen our understanding of our own existence. But before answers arrive, we continue to listen to the quiet possibilities of these ocean worlds, letting them fuel our sense of wonder. The fragile spark of consciousness that we carry on Earth had humble beginnings in places perhaps not so different from these alien seas. If life does exist in an ocean beneath the ice of a distant moon, what might it one day become, given enough time? This line of thought brings us back from the search for simple life to a profound mystery here at home: the emergence of consciousness. Our exploration of life's potential in the cosmos invites us to reflect on that delicate flame of awareness that has arisen in at least one species on our planet. In the next chapter, we shift our gaze from hidden waters to the elusive phenomenon of consciousness. the most fragile and wondrous spark known to us. Consciousness, the awareness of self and surroundings, is perhaps the most enigmatic phenomenon our universe has produced. From inanimate matter arose a mind that can ponder its own existence and marvel at the stars. How fragile and unlikely this spark of sentience seems in the vast, cold cosmos. On Earth, it took billions of years of biological evolution for consciousness to flicker into being, and even now it resides in a delicate form, dependent on the intricate workings of our brains. In humans, this spark allows us to experience joy and sorrow, curiosity and creativity, yet we know so little about how it truly works or why it came to be. The emergence of consciousness is not guaranteed in the story of life. For most of Earth's history, life got along without self-awareness. Simple organisms lived, reproduced, and died under the sun or in the deep sea without ever perceiving themselves. Even as life became complex, it is only in a relatively few species that anything like what we would call consciousness arose. Our own lineage, primates, and ultimately humans, achieved a particularly rich and reflective form of mind. But this development could easily have gone another way. If events in our prehistory had differed, perhaps no creature would exist who contemplates meaning or the cosmos. The rarity of this trait makes it feel precious, a tiny candle flickering against a great darkness. We also recognize how physically fragile consciousness is. It depends on the healthy function of an organ, the brain, which itself can be disrupted or destroyed so easily. A brief lack of oxygen, a single traumatic injury, or a few microscopic changes in brain chemistry can snuff out awareness or alter it profoundly. The difference between a thinking, feeling person and an unconscious body can hinge on the smallest of physiological details. Knowing this, we can't help but realize that our self-awareness is a tenuous state, one that the vast forces of nature do not especially safeguard. It exists in spite of the universe's indifference, a flame that must constantly resist being extinguished. Beyond the individual, the spark of consciousness is collectively fragile on a planetary scale. All the conscious beings we know of, humans, and perhaps some of our fellow animals to lesser degrees, live on one small planet. A catastrophic event, like a large asteroid impact or nuclear war, could potentially end the only known consciousness in the cosmos in a very short time. That awareness, which took billions of years to emerge, could be snuffed out, leaving the universe once again without a voice to appreciate it. This vulnerability lends a poignant urgency to our efforts to protect our world and to perhaps spread life beyond Earth. We carry, in our minds, a rare treasure, the ability of the cosmos to know itself, and it rests on precarious ground. Consciousness is also mysterious in its depths. Science has yet to fully explain how the electrical and chemical activity in brain cells gives rise to the rich inner world of thoughts and feelings that each of us experiences. This hard problem of consciousness leaves us humbled. We carry within us something we do not understand. We are at once the investigator and the very phenomenon we seek to investigate. Throughout history, thinkers have puzzled over whether consciousness is purely a product of biology, or if it hints at something fundamental about the universe. We still don't have the answers. What we do know is that consciousness allows us to reflect on existence itself, turning the universe back onto itself in contemplation. It is remarkable to consider that the atoms in our brains were forged in ancient stars, and now those atoms have organized in such a way that they can think and feel. In us, the universe has achieved a form of self-awareness. This realization can be both awe-inspiring and sobering. On one hand, It means that we are literally the cosmos made conscious, a way for the universe to reflect upon its own nature. On the other hand, it underscores the responsibility and fragility that comes with that awareness. We are conscious beings capable of great creativity and understanding, yet we are also capable of great folly, and our continued survival is not guaranteed. Our consciousness also connects us to each other. Empathy, love, communication, these arise from the fact that we are not just biological machines, but beings with inner lives, recognizing the inner lives of others. That delicate spark of awareness enables us to share experiences, to imagine other perspectives, and to find meaning in relationships. It fuels art and science, philosophy and spirituality, all the pursuits that spring from minds reflecting on more than mere survival. In the grand cosmic scale, these may seem like subtle, intangible things, yet they are the very color and texture of our existence. They are what make life not just a biochemical process, but a conscious journey. When we gaze up at the night sky, it is the consciousness within us doing the gazing. Stardust, contemplating the stars. That awareness can feel transcendent, as if bridging the internal and external, the microcosm of the mind and the macrocosm of the universe. It is a reminder that however small we are, something profoundly special is happening through us. Still, we must remain aware of how delicate this phenomenon is. Unlike the stars which will burn for billions of years, a single conscious mind can wink out in an instant, and the collective flame of intelligence on Earth, if not tended, could someday fade. Yet, there is resilience in the story of consciousness too. From the vulnerable beginnings of early humans, beset by predators and natural disasters, conscious thought has endured and grown. We have used our minds to create tools, to cure illnesses, and to extend our reach beyond what our bodies alone could achieve. Each generation passes the light of awareness to the next through teaching and storytelling, attempting to preserve and expand knowledge. In this way, consciousness can be seen as a continuum, a torch carried through time. It has survived ice ages, plagues, and wars. This resilience gives hope that, despite its fragility, the spark of consciousness can continue to burn brightly if we nurture it. In contemplating the fragile spark of consciousness, we circle back to the miracle of being, that we are here, that we feel and think, in a universe that might have easily been cold and unknowing. Our journey through the mysteries of deep space and life has led us to appreciate this spark as something truly precious. As we prepare to turn our focus to the miracle of being itself, we carry with us a gentle reverence for the unlikely union of atoms and awareness that defines us. In the next chapter, we will take a soft glimpse at this miracle, the simple, profound fact of our existence, and the beauty inherent in just being alive and aware. This simple fact is in many ways a miracle when set against the backdrop of an unconscious universe. Think of the countless accidents of history and nature that had to fall into place for us to exist here and now. The atoms in our bodies were born in stars long ago and scattered across space. Earth formed at just the right distance from the sun, preserving liquid water. Life sparked from lifeless chemistry, endured billions of years, and eventually, against all odds, one branch of life gained the ability to ponder existence. That chain of events is so unlikely, and yet it happened, culminating in the personal miracle of each of us experiencing this moment. Sometimes In the rush of everyday life, we lose sight of how extraordinary it is simply to be. But when we pause, perhaps looking up at a sky full of ancient starlight, we can gently remind ourselves that our very ability to wonder is a product of cosmic processes, eons in the making. Every heartbeat, every thought, every emotion is a testament to an unbroken lineage stretching back to the first living cell. We carry the legacy of the cosmos within us, and through us, the universe can appreciate its own beauty. In each breath and each heartbeat, there is something wondrous, the universe living and aware in the form of a human being. This perspective can fill us with a quiet gratitude. The elements that form our bodies, the water that quenches our thirst, the air that fills our lungs, all were provided by a universe that knew nothing of life or consciousness until life emerged. Yet here we are, tiny specks of organized matter, capable of love and imagination, of memory and dreams. Realizing this can inspire a profound sense of connection and reverence. We are connected to the stars that gave us our substance, to the earth that shaped and sustains us, and to all living beings with whom we share the spark of life. In that connectedness lies a gentle kind of meaning, that we are not isolated fragments, but part of a vast, enduring tapestry of existence. The miracle of being is not a miracle in the supernatural sense, but rather a natural miracle, something so marvelous and improbable that it feels magical, even though it arises from the laws of physics, chemistry, and biology. It invites us to cherish our life, and life in general, knowing how rare and precious it may be. It also encourages humility. We are special, but so is every other living creature that shares in this unlikely gift. Just as importantly, this awareness calls us to responsibility, to care for our planet and each other, because we recognize how irreplaceable the phenomena of life and consciousness are once lost. As we softly contemplate the miracle of being, we sense a kind of duty to savor it and protect it. Each day that we wake up to a new morning is another verse in an incredible cosmic story. The atoms of our bodies have traveled through time and space to be here now, coalesced into a form that can reflect on itself. Perhaps the greatest tribute we can offer in return is to live consciously and compassionately, to use our brief flicker of awareness to appreciate, to learn, and to love. In doing so, we honor the countless stars and ancestors that made our existence possible. Our journey through the cosmic enigmas, from the birth of stars to the emergence of life and mind, has led us to this gentle moment of reflection. It is not a final conclusion, for the story is never truly over. There are always new mysteries on the horizon and new questions arising as we deepen our understanding. The miracle of being is, in itself, an open-ended wonder. In acknowledging it, we don't close the book. Rather, we open our hearts to whatever comes next. With calm curiosity and reverence, we carry on, knowing that as long as we live and think, the universe is not done exploring itself through us. And so, we continue our exploration, carrying forward the sense of wonder and humility that this journey has instilled. In the vast darkness of space, our awareness remains a gentle light. The story goes on, and as we move quietly into the next chapter of this journey, we do so with the understanding that every ending is but a pause before a new beginning. The cosmic enigma persists, and our quest to comprehend it continues, one soft, curious step at a time.